Let's wait for everybody to take a seat. Are you ready for a deep dive? Because this is going to be a deep dive.
Yeah, we have to warn you here. We will start a little bit higher level up, but we will hopefully then get into Linux kernel. We will get into assembly level, compiler optimizations, compiler graphs,
Bit twiddling,
bit twiddling, SWAR, mathematics, everything. And we are really excited that so many are here. And so let's get started. So Roy, who are you and how did you get to this OneBRC?
Yeah, so my name is Wuerthinger. I work at a company called Open Value. We do contracting work. If you're in the Netherlands and you need a developer, come to us. And if you want to work on cool Java projects, talk to me afterwards, basically. What about you?
I'm Thomas. I'm the GraalVM project lead. And when the OneBRC started, so this 1 billion row challenge that was created by Gunnar Morling, I saw the first submission from Roy, and I found it very exciting, this team spirit and the spirit to kind of get Java here to the next level of performance inspired me to get into the challenge itself. And this is how sort of this got started, and this is how my January got filled very quickly with a lot of work.
Yeah.
And how was it for you, Roy?
Yeah, no, same. We'll go into the first days of the contest later. Basically, we both wanted to talk about this topic at Devox, and Gunnar, is he here, Gunnar? Not yet. I'll be doing a talk with Gunnar on first day as well about the same topic, but more from an organizer side. Like, he came up with this contest, and basically what happened during this crazy month for him, because he gravely underestimated the time and effort it would take to run a simple contest. So
right, absolutely. I think it was for him. It went viral very quickly and was surprising. But yeah, if you want to hear more about the community aspect of the context, there will be the talk from Gunnar. But in this talk here, we will delve into the very technical details, and we will try to get you the view of participants of the contest, how we optimized the programs, and not just optimized for this specific contest. We will try to also. We hope that everybody learns in the end something that they can use for their own Java applications as well, should performance be an issue for them.
Yeah, basically Stefan said, well, you guys, we can't do 3 conference talks, so make a deep dive. So now
exactly. So Stefan invited us for this deep dive. We are talking for the first time together. So, we will manage this. And if you have questions in between, you're free to ask them. You can interrupt us.
Exactly.
And yeah, let's get going.
We have the time. So
we will at the beginning just have a general introduction to the contest.
Who here competed in the OneBRC challenge? Anyone?
Oh, you were all just watching, right?
Oh. So for me, basically, it started back in 2023. Last month, I was doing the Advent of Code. Who's doing Advent of Code? More hands, good. So I was already programming every day in December. And I naively thought, well, January will be easier because no contest running. So I woke up at the 1st of January with a little bit of a hangover because New Year's Eve. And this tweet dropped, and it was by Gunnar, and he said, well, there's this 1 billion row challenge. So how fast can you aggregate 1 billion rows using modern Java? Sounds interesting. So let's take a look. What is this challenge? Well, you get a file with 1 billion, so that's 9 zeros, 1 billion rows. And you have to print out some results, and you can only use vanilla Java. So no frameworks, no libraries, just one single Java file, that's it. Sounds easy enough. So the input, what does it look like? Well, like I said, it's 1 billion lines of data, and every time you have a city name, then a semicolon, and then the temperature. And this temperature is between minus 99.9 and positive 99.9. Just 1 decimal precision. And you can see an example here from Hamburg and St. John, etc., etc. That's it. What do we need to output? Basically, for each of the stations, we need to output the minimum temperature in this entire file, the average temperature, and the maximum temperature. And this is the specific output format. And if you say that looks a bit weird, it's basically a map.toString, because Gunnar was a bit lazy, I think. And this sounds like a very good way to do it, but in the end, nobody was using Java's hash map, so we all needed to implement this bracket, etc. We'll get there.
Yeah, and so this is how how you saw on Twitter the challenge starting going, and I was also waking up from my New Year's hangover, and I go on Twitter and I'm like, there's this viral Java challenge for Java performance, and as the GraalVM project lead, of course, we're very proud of our performance. So my first thought was like, hopefully Graal is gonna be good at this. This is how we then I got very excited about the challenge. And I was very surprised because before I even entered the challenge, I saw Roy as one of the guys on the top leaderboard, and he's like, I'm using the Graal JDK. I'm like, oh, thank you, Roy. We didn't. That's awesome. And so what happened is that even initially, when people started submitting their first versions, they were testing with different JDKs, obviously, to check different performance characteristics. And when people were starting using the Graal chat, it gave them actually already a free win without changing any code. Because the Graal chat compiler does more optimizations, and specifically for the for this stream API code that Gunnar was putting into the reference implementation, it is already faster. So I measured this on my computer in preparation for the talk, and just switching to the Graal chat compiler gave you 8%. So the regular implementation on my computer is 125 seconds, and then switching to the JIT compiler is 8% already plus. You do nothing, you just change the JDK distribution to Oracle GraalVM.
Let's take a look at the
yeah,
reference.
if you look at let's look at you want to look at the reference implementation, yeah.
So this is the reference implementation. This was given by Gunnar. It runs in about 4 to 5 minutes. It differs. Basically, it uses file.lines to read everything using a single thread, and then it uses streams to collect the results. So you can see there's this result row, the thing that we need to output. It has the rounding that we want, the min, the mean, the max. We've got this aggregator, which for every city has the min, the mean, the max. The min, the max, the sum, and the count, so you can calculate the mean. Basically, it starts at the bottom. We do file.lines to get all the single lines as a stream. Then we put this entire thing into a map. And to do this, we use this big collector. So what does this collector do? It has 3 parts. The top part creates a new aggregator when you have this input line. So it takes the min, the max, and the sum and the count, and it increases the count by 1. It adds the sum, and it basically takes the aggregator, puts in a measurement. The second thing is when you have 2 aggregators, because this can also happen. This can also needs to be combined. Basically the same thing, 2 aggregators, you min the mins, you max the max, add the sums together and add the counts together, and you're done. And the final thing is mapping to the result row, which is basically the same thing as we saw on the previous slide. And that's it. We can print the output. The output is the map itself, toString, and that works. Runs in about 5 minutes. Should be fine.
Oh yeah, but you can then switch your JDK and you're a little faster. Now, apart from switching the JDK, so if you look at the agenda here, we will, over the course of the deep dive, go over each of these entries. So this, let's maybe describe a little bit what this agenda means here. What I did in preparation for the talk is I took the winning solution of the OneBSC, and I created snapshots for every submission, for every major submission on the contest. And this shows the progress of that winning solution over time. And then I benchmarked the winning solution and described the changes from one version to the other. And in this way, during the course of this talk, and also if you look at this repository that we put up for this, you will see not only the final version of the winning solution, but you will see every single optimization applied and how much impact it has. And yeah, so the first optimization applied is just use a different JIT compiler. Now, apart from the JIT compiler,
I tried different JVMs.
So
yeah,
it's a little.
but this works, right?
Right.
That's weird.
I'm confused that the screen here doesn't show what the screen here is showing, but okay. I guess
Well,
you guys see what the screen here shows. Okay, good. That's good. Yeah. So the JIT compiler provides a higher throughput, but very soon in the contest, as some of the solutions were getting more optimized, already GraalVM native image was better at the contest because of the startup characteristics of it. And this is, maybe surprising for some people because sometimes, people think, okay, GraalVM native image is only good for the 5 millisecond startup or 10 millisecond startup, but it turns out even for this type of programs that run for 3-4 seconds, the faster startup gives you then a total faster time of the overall process. And that's why even in the early days, native image already started to be a win. Now, the contest was measured using Hyperfine, which is a benchmarking tool. Hyperfine takes a command and it executes it multiple times, and it will get you the average time it was running, and it will get you the variance. This is, of course, very important with benchmarking. Whenever somebody sends me a benchmark result or a performance result, I will always ask, did you repeat the experiment more than once? Because often people just send you one time the experiment and think, yeah, this is my result. It's very important to repeat the same experiment multiple times, so you will understand what's the noise in the system. And if you run a command with Hyperfine, it will get you this information. It will get you the average, and it will get you information on the noise on the system. And I'm taking here the V1, which was the first submission. It's just generally optimized, and Roy will talk about what the optimizations in this are. But when you take this V1 and you run it in JVM in JIT mode, it takes on my machine 1.7 seconds on average, and if you run it in the EOT mode, if you create a native image out of it, it will run already in 1.1 seconds on that machine. Now, this means it's 1.5x better, which is great. But what is even more important, and this was more important as the contest progressed, is that it's not just 1.5x better. The variance of the performance when you start it multiple times is 5x better. And this is a very important aspect about EOT compilation that is less well known. It's not just you get good startup and low memory footprint and whatnot. You also get much more predictability, because in a dynamic JIT compilation environment, whenever you start the program again, it could yield different results. It could yield different decisions during compilation and so on. And in the contest, one of the big advantages of using native image, apart from the performance in general, was that you could very reliably test whether the new version was 2% better or 2% worse. And when you start to kind of optimize in the end, that was very useful. And here it's 5x better. If we then use the same Hyperfine experiment on a slightly more advanced version, which is now version 3, it was a slightly faster, better optimized version, then you have here the advantage to use native image got better and better, because you have less work to do, so the startup matters more. And the variance is just a huge difference. It's a 10x variance here. So if you ran this on JVM mode, the plus minus in performance you got was 200 milliseconds. And the 200 millisecond difference on a 1 second means between runs you already have 20% difference, plus minus, which then makes it very hard to understand, is my new version better or worse by 5%. And in native image here, the variance is 10x better, so it's only a few percentage variance between runs. So if you run this a couple times, you have a very good understanding whether the performance is better or worse now. And this predictability and reduction of variance is a very nice property of EOT compilation that makes your whole cloud environment more predictable, more reliable, because it reduces the outliers. And as we progress down the line of getting deeper and deeper, we'll see how we, in the end, we're trying to save one machine instructions per row. And at that point in time, having such a stable environment was a real advantage here. And that's why Graal and GraalVM native image was a very useful tool for the contest. And we were very happy about that, of course, to the extent that people suspected Gunnar, this was a marketing ploy by the Graal team to set up the whole contest. But yeah, we deny everything related to that.
That was just coincidence.
It was just a lucky coincidence. That's right.
Why is it so slow? It's really weird.
Well, I need to look at this screen. Yeah.
Yeah.
So, in terms of creating the native image, this is the shell script that Roy was using. Now he put this in the slides, but I actually wanted to delete that slide because there's a bunch of options up there that we are not recommending for anybody to use at home. So I will just talk about, and they are not very important. Maybe some of them gets you 0.3%. Like there's one up there which is -gen loop save points. If somebody's a super expert, might know that. Yes, maybe it gets you half an instruction less, but it doesn't matter much. Now these are the native image options that are recommended, and that's the one that I was using in my solution in the end, because I wanted to submit a good solution, but I also didn't want to cheat by using some flags that are not supposed to be used. Now, native image has an optimization level option similar to GCC that is here 03. And if you want maximum performance, that's one thing to certainly use in your app. Then I'm using another flag here, which is tune inliner exploration, which is a value between -1 and +1. And if you put it to +1, it means explore a lot. Because in the end here for this small program, we didn't care about the image size. We cared only about inline everything, make a huge compilation, and we'll later see how huge it was. But in this scenario now, we are putting inliner to the max. And in this way, we will also not have to worry about some helper function not being inlined, which would be a big performance hit. The next parameter here would be march equals native. This is also a parameter similarly available on GCC or Clang. And so they're we are trying to get to the machine. We're targeting the machine architecture, meaning we are using AVX and other properties of the target machine.
The garbage collection is really fun. Like, what kind of garbage collection would you want to use in this environment, right? Who here has heard about the Epsilon garbage collector? What does it do? Nothing. Exactly. It's perfect. It's the nothing garbage collector. It does something. It allocates. Okay, sure. But it doesn't clean anything. It doesn't run. It doesn't do anything. So it's perfect for this contest.
Yeah, it's perfect for this contest. And I mean, the interesting thing is this. Like, why does it matter which garbage collector to choose for the performance if the garbage collector anyway does nothing? Now, the reason is that even if you use your G1 GC as an option, which is the typically recommended option for native image, it would not make a garbage collection. But G1 GC requires very complex write and read barriers, which is code that is inserted before and after memory accesses, reads and writes. And this blows up the machine code size, like reduces instruction locality, and it has even a certain overhead because it's some instructions that need to be done in order to check for some garbage collection concurrent activity. So this is why here going for epsilon GC makes your code smaller and faster. And despite the fact that garbage collection will never actually run. And then the final parameters here is just using a class parse, like that you need to, what is my application? That's how you tell native image, this is my class parse for my application. This is the name of my target output binary, and then it's the name of the main class. Because when you invoke native image and you create a native image out of your application, then you always just specify the same things you would specify as if you would run a Java application. You specify class parse and main class. And thankfully, because the program is pretty small, the image generation is relatively fast. So my machine creating a new image was about maybe 8, 9, 10 seconds. So even for the development turnaround, it was okay because the program was so small. Yeah, it's still like this is the output from the image generation. It will output a bunch of statistics which are not relevant for you, and then it creates the native image, and you can go from there. But then, yeah, let's talk about the high-level optimizations of how the first, and you can see this if you look at this this delta line, if the delta column, right? This V1 that Roy will now describe, it's 95% faster than the reference implementation. So just by applying this, you get 95% of the way, and then it sort of gets harder and harder, but the return of investment gets lower and lower, of course.
So this was actually on the 1st of January. I saw that Gunnar posted the challenge, and I initially thought, well, I should wait until the last day and submit something. But on the other hand, why not just submit something, something suboptimal, so that other people will say, wait a minute, I can do better, I can beat Roy. So initial commit, I committed something. I wanted to make some things parallel, because why would you want to use a single thread if you have a machine with 8 threads? And this already, on my machine, this one little change brought it down from 5 minutes to 2 minutes, which is already great. And this was something that the entire contest, it was all seeing what other people were doing, learning what they were doing and why they were doing that, adopting your own code, adopting your own strategies, trying different stuff, experimenting. And this was all done out in the open. Like, I submitted something on the first day, and everybody could see my code. So there were no secrets, basically.
Absolutely, and it was a collaborative open source effort. I think everybody was copying from everybody the best versions, and collaboratively trying to get the max out of Java.
And that's why I learned a lot, because if everybody waited until the last day and then submitted their solution, I wouldn't even look at all the solutions and look at the things, and I would probably not have learned as much as I learned.
Yeah, no, and it was certainly like part of the fun of the contest to see what Roy cooked up next, and
yeah. So my first change, basically, I added .parallel. So it's not the only change I made. Basically, read the file, but process everything in a parallel stream and not in a single thread stream. You do run into one issue. You can't use a regular map to write things in parallel, because then you get concurrent access problems. So I needed to basically use a concurrent map. But also, instead of using, the old implementation was using string.split to make a new array every time. And I thought, well, why would I make a billion arrays? That's not very convenient. Why not just find the pivot, read the key, read the measurement, and do that, instead of making a new array every time? And that's it. That's basically the only thing I did. I was using a stream, sorting that and printing that instead of using a map and doing toString. This was actually a little bit faster. No idea why. I just tried a couple of things. And that already made the code run twice as fast. And then 2 days later, you can see my own change log. A lot of things happened. I already went from like 62 seconds down to about 2 seconds on my local machine, which is an M2 MacBook. We'll come back to that. So on the target machine, it was running in 23 seconds at the moment. So what kind of changes did I do? Well, one of the biggest ones was we were using doubles as temperature, but why? These things have 1 decimal precision. If we just multiply by 10, it's an integer, and we can use integer math. And integer math is just way faster on machines.
Yeah, and this was the single most important data structure optimization on this contest, and it kind of shows if you look at the impacts that when you go at the problem, you will not first look at some low-level code optimization. You will look at like, can I use a simpler, more efficient data structure? In this case, using int instead of double is much faster on modern processors.
Yep.
And so that's why this was huge impact.
Yep. Another thing that we did was actually breaking the file up into equal parts. So instead of going through the file from start to end and having these little lines be processed in parallel, we just break it up into whatever amount of processors we have. So in this case, we had 8 processors. So we break this entire file into 8 parts, and we give this part to a process. So we spawn a thread, you process this part. Now you get locality. So one thread is reading a part of memory, and it's actually processing each and every step of the thing that is being put on that CPU, thread, core, thingy. Terminology, not my thing. You do need to watch out. You can't just divide it into 8 equal parts. You need to find the end and the start of each record. Early on, we did it in this way, where you first single thread process and cut it into 8 pieces. Later, actually, it turns out you can also delegate that to the processors and do that in parallel as well. So you just say start around here, and the process itself finds where it needs to start. That's another parallelization optimization
Right.
you could do.
Yeah. No, absolutely. But I mean, this parallelization gives you 8x speed up. I mean, essentially the number of processes available, and so the parallelization and the data structure optimization together is what gives you then this 20x over the reference implementation, which is the easiest win. And I think one thing to mention here as well is, well, this find segment might not be super optimally implemented, but that doesn't matter. Like in this whole segment of the problem, I think it was also during the contest quite important to figure out, there's only 10-20% of the code where the performance actually matters. And you need to focus there. And the rest you can just program in whatever way you like, because the performance, how you find the segment here, for example, you can just linearly scan through the file with a file pointer. It doesn't matter, because you will only have 8 segments, and it doesn't matter in the grand scheme of things.
Yeah, focus on the big thing first and optimize those little things later.
Right.
Perfect. So one thing we did use were memory mapped files. This is a JEP that has been added in 21 or something, Java 21. What we can do, instead of opening a buffered file reader and going through this file, we can basically tell the operating system, we want you to basically give me a byte buffer in this case, and this is the file. And the operating system itself take care of reading the file and making sure you get the actual data. So this is very easy. You can say files.new byte channel, and then we can say .map. And now, in this case, we get a byte buffer, and we can basically read in this byte buffer and get the actual data that is there. You don't need to worry about any file stuff, file I/O.
Yeah, and the memory mapping was definitely the fastest way to get the file into Java. Because later we will see there was also some problem with memory mapping. And because of that, and because of the page faults and so on that are involved with memory mapping, I did, during the contest, some experiments of try to actually read the files in some shape or form without memory mapping. But any such experiments showed it was always slower. I could never make it faster than the memory mapping from the operating system. So if you read a large set of data from somewhere, definitely go for the memory mapping.
And it doesn't even, correct me if I'm wrong, but it doesn't even matter if the file is larger than the amount of memory you have, because that's just something
Correct.
the operating system does for you.
Yes.
Even if you have like a 200 gigabyte file, you can still use memory with files.
Yes,
It
yes,
doesn't.
yes. I mean, it can even work for mapping in a larger file the memory you have. And of course, it's super efficient if you only use part of the file or if you jump around the file, because the operating system will automatically bring in the pages that are necessary next with some heuristics. But I mean, even in this kind of worst case scenario for memory mapping, where you actually need to just sequentially get everything in, it's still the fastest in Java to do the memory mapping and not use a regular read from file.
Yep. This was after.
Yeah, this is where Roy wanted to stop the count. Yeah. So.
Yeah. So early on, you can see some familiar names here. I'm not going to spoil who won eventually, but it wasn't me.
Right, but yeah, so this was the first leaderboard on January 7th, so very early.
But you can already see we're already at 6 seconds here, so.
Yeah, no, pretty good, and I like the JDK that's used for the top 2 solutions there as well. Yeah, absolutely.
Yeah.
And but there were many more solutions to come.
We'll come back to number 3, by the way. His name will come back, and the reason he's using OpenJDK, we're also coming back to that. Yeah.
Right, and yeah, given that I was only second after Roy here on this previous, slide, as you could see, I was thinking, how can I improve my solution further? And I felt a little guilty, but after thinking about this a little bit more and knowing what the compiler produces for such a byte buffer access, I had to go with sun.misc.Unsafe.
Sorry.
Yeah, we're sorry about that. Now, unsafe allows direct memory access, like in C. So this means there is no bounds checks and there's no checks on safety of the access. But specifically for accessing a memory mapped file, it seems a very natural way to access this type of memory, because the memory itself is more native memory that's managed by the operating system. So accessing it with unsafe seems more natural than going via any type of Java constructs.
And even versus a byte buffer, for example, even a byte buffer checks if you are reading something from inside the byte buffer, which is perfectly fine. It should absolutely do that, and you should never use unsafe in your production code. But if you want the maximum speed, you don't want to. My code is perfect. It doesn't read outside of the byte buffer.
I would say it's okay to use unsafe in very special occasions. You just need to be aware that the typical Java safety guarantees of array bounds exception and making sure your program cannot crash, they don't apply anymore. So if you make now a programming mistakes, you would bring down the process, and otherwise you just get some exception, right? Now Java in general wants to move away from unsafe, because there could be in the future ways on how to access memory efficiently, and native memory specifically efficiently. But there's currently some work going on this in the memory API. I wanted to use the memory API, kind of be a good citizen first.
So you've got byte buffer, but you also have memory segment. Like those are the two alternatives.
Yeah, exactly. Right. Yeah, and byte buffer was the one that I could understand the easiest, and memory segment I was also trying. The problem is that memory segment still has a lot of checks in there. I was looking at the memory segment in this is the ideal graph visualizer, which is the visualizer of compiler graphs of Graal. And, well, this is for one memory access. And you can see that for one memory access, it does a lot of checks. It checks some scope, it checks whether it's in bounds and so on. And only at the very end is the raw load instruction at the very bottom of the screen. And if you go with unsafe, you only have that last instruction, which is, of course, faster. Now, thankfully, Intel machines are really good at actually making bounds checks that go always one way fast. And Intel speculative execution is one of the reasons why, even if you have a lot of checks in the program, it's reasonably fast. But for this contest, and reasonably fast wasn't the way to go, so it had to be unsafe. And so this is getting unsafe is already a little awkward in Java. I think it's intentionally so. You need to make some reflection going and get this unsafe out of some field of the unsafe class, because it's typically not accessible to you. And but then you can just use unsafe.getByte and then a long address to access a certain piece of memory in that file.
Yeah. So in this case, we use a memory map file. We say we read this file as a read only, and we just want the first address. And then we get the memory address of where our file is, and we can just read bytes and integers and longs and strings and other stuff from that memory.
Yeah, and
Really
for a memory mapped file, this type of API, like, it feels very, very natural. Now, I wanted my code not to look so unsafe. So early on in the solution, I did a little change here where I'm wrapping the unsafe into a scanner class because I wanted to hide the dirty unsafe access, and I wanted to make it look in the code more like it's on the right here, where you have a scanner equals new scanner, and then you scan get long, and maybe people don't realize there's unsafe underneath it, right? And that made the code, of course, look much nicer. Now, the one thing you might ask yourself is like, but you have an object allocation, you have an interaction, like, isn't this slower, right? But this is where, thankfully, Java JIT compilers, and specifically Graal, is actually very reliable in reducing the object allocations if they're local only. So this scanner object will never be allocated in real, because the compiler will remove the allocation and just treat the fields of the object as local variables. And this was on the one hand made the solution look nicer, and we will later see, as we made the solution more complex in the very last steps of the contest, it was quite important to have this scanner object in place, because certain code transformations would have been much harder to do without such a scanner object. And it shows here that in Java you can still be object-oriented. You can still create objects, use them locally, and the performance overhead of doing so is zero. Like, I mean, if you on the scanner.getLong, like, the scanner holds actually the position. The scanner has like a long pose field, a position field, and the position field is the field that moves through the file. But that field is never actually a field when it's running in the VM, because the whole object gets escape analyzed and the field is just a local variable. So when you're actually then getting the getLong, or I'm getting a field from a value from the scanner, I will not have a field access. Now, one of the things that I feel like we should develop more in the Java world is like better tools for highlighting this to the programmer, because it's at the moment very hard as a programmer to figure out whether this scanner object in Java actually got allocated or not. And so I could figure it out, because I could look at the compiler graph and search if there's an allocation node, and if there's no allocation node, everything is good, right?
I could not.
Yeah, he could not. So yeah, and that's unfair, of course. So that's one of the things. And on the other hand, we don't want. I will later in the deep dive, I will go to the compiler graph and show you how it looks like. But you will then also see why it's not a good idea to expose the compiler graph directly. But I think what you want to get to is, and this is some features we're working for GraalVM, is where you will get some higher level form of feedback on these aspects. And in this way, we could use unsafe here, but still have a nice Java code. So that was the thing. And if you look at the performance benefit of this V2, which is this unsafe version, so using unsafe, just going from the byte buffer to unsafe, was a 25% win. So I didn't change anything in algorithmics between those two versions. and it was 25% faster overall using here unsafe versus the byte buffer. But obviously, Roy got very motivated, and so we had to go further.
Yeah, so this was also one thing you did, right?
Yeah. So this was
one thing we needed to do very often was if there's a certain city name, Hamburg, for example, and there's something that you're now parsing, you need to compare these things. Sure, you could compare two strings together, but what you can also do is just load these bytes 8 at a time in a long value and just compare the long values. So that's the same thing as comparing 8 bytes at a time with each other. And that's basically what you're doing in this code, right?
Yeah. In this code looks a little funky. Now, it doesn't look funky to a compiler engineer because compilers, when they are unrolling loops, they are actually producing exactly this code shape. So the compiler, I mean, I could have probably also gotten this by guiding the compiler correctly, but the compiler uses heuristics on when to unroll or not unroll, and in this case, I basically manually did that compiler transformation. So for the program itself, it would be enough to just have the loop on the bottom here. It's the loop over the bytes, right? Yep. But you then are effectively taking that loop and you're peeling. It's called loop peeling, where you take the body of the loop and you copy it before the loop. Whenever you have any loop, you can always copy the body and copy it before the loop. Because that just makes sure that the first iteration is before the loop, and then the loop starts with the second iteration. But you can do that actually with any loop you like. And if the loop, for example, has a very small number of iterations, it might improve the performance of your code. Because the VM will have an easier time profiling the first iteration compared to the actual loop, and it will likely produce better code for it. Now it will make your code look a little strange, and you'll have to get through the code reviews and things like that. And somebody will tell you, like, why the hell did you copy this code? And this is not necessary. But then you can point to the one BRC solution and say, like, look over there, right? So in the end, what we did here is we copied the body of the loop upwards, and then for the cases of 8 lengths of city, we are comparing not a byte, but we're comparing a long. And for the cases of city name length greater equals 4, we're comparing an int instead of a byte. And this, of course, makes things faster because you have less memory accesses and you have less instructions to worry about. But so this was like, as a compiler constructor, I did this type of optimization. But then I think Roy and also Quan, they were like, okay, we can get this a little further. Yep. And that's where then the full mathematics stuff comes in with SWAR scanning and branchless temperature parsing.
Yeah, actually, shout out to Francesco. He was actually the one who messaged me on Twitter, or X, Twitter. He said, well, you should look at SWAR. I had no idea what SWAR was. So what is SWAR? So instead of processing each individual character or byte at a time, why not do 8 at a time? That's faster, right? Turns out you can do this. SWAR stands for SIMD as a register. No idea where the W comes from. And SIMD stands for single instruction multiple data. Where does the W come from?
I know.
Within.
Within.
Nice. Now I know.
Very sophisticated.
So, for example, if we have this piece of the data, so we have a city name, Tokyo, then we have the temperature, minus 18.3, then we have a new line, then we have Amsterdam, etc., etc. So this is all in the memory, and we read the first 8 bytes in a long value. And if you look at what Java does, if you display it this way, then it's actually flipped around. But so I flip the bytes around in this case. Makes it a little bit easier to use the examples. So next, we make a mask, because we need to know where this semicolon is. And the separator is just repeated 8 times. So we also do that in a long value, because a long value has 8 bytes in it. What we can do now is this small piece of code, find any pattern. It looks like magic, and if you don't know how it works, it is magic. So basically what we do first is that we XOR these 2 values together. And XOR basically takes the difference between 2 values. So you can see where the separator is exactly the same. It has the same bytes. It turns into all zeros. What we can do next is we have this magic number, which is basically the least significant bit. We can subtract it. And if we do this, and if it was all zeros, it becomes all ones. And it flips the one like from the previous byte. What we can do now is that we can take this weird number with all ones, we negate it, and we end it together with the mask. And this already looks pretty good, because the only way that the most significant bit is a 1 at this point is when they were all ones. So now we can end it together with the most significant bit, and the only way that this bit is 1 if it basically is when all the bits were the same. So this code, if you run these steps, and it's basically 1, 2, 3, 4, 5 operations, now you've basically you find that it can only be 1 where the pattern is. And now if we take the number of trailing zeros and divide it by 8, but dividing by 8 is the same as shifting 3 places, so then we get 5. And actually 5 is the length that we want, because that's where the separator is for the name Tokyo.
Right. And so one thing I think which is also important to know here is this number of trailing zeros or number of leading zeros are functions in Java that get intrinsified into the corresponding x86 instruction that is very, very fast.
Yep.
So in an x86 processor, figuring out where is the first 1 in a bit pattern, or where is the last one in a bit pattern, is a very fast instruction. And you can have access to these instructions from your Java programs guaranteed via this long dot number of trailing zeros or integer dot number of trailing zeros methods.
Yeah, gets turned into a single machine instruction.
It's a single machine instruction, it's super fast. You will not notice just by looking at the Java code, because the Java code for this would be very big, but the compile intrinsifies this.
Yep.
And therefore, in a lot of these patterns, it's always about like, well, can I somehow bit shift and XOR and end things around such that with counting the number of leading or trailing zeros, I get some information.
Yep. A second thing, we mentioned it already, is going stringless. Your comparison that we had before was already doing this. We were looking at basically, if you have a string, then you have all these bytes and you need to allocate this, but we don't. We can just keep the memory that represents the string, and we can look at it, for example, like this. We can look at, are these 8 bytes the same as these 8 bytes in one single comparison? So this is very, very fast. The only moment that we actually need to turn these things into strings is when we output it once at the end. We don't have to do this a billion times. We only have to do this, I don't know, 100 times, because there were 100 cities. Major speed up. This also comes into play with branchless programming, and I want to explain it with a very simple example here. So our CPUs have a big pipeline of instructions that it wants to execute. And it's your job as a programmer, or the code's job, to fill this pipeline. You need to fill this pipeline and make sure that the compiler knows, the processor knows what to do next. And this works perfect until you encounter an if statement, for example, or a for loop with a comparison. This is where you need to branch. It can go either way. So your CPU can no longer predict what's going to happen next. And this is always like a bottleneck. And we'll come back to that later. So this is a regular absolute value. So integer x, we want to have the absolute value. Well, we can look at it. If it's a negative number, return the opposite of the negative. So that's a positive number. And otherwise, return the positive number. this code works perfectly, and I think this is also, Graal will probably be able to translate this into something very efficient, but this has branches. You can also do something like this, which is a bit weird, but we take our number, we shift it all the way to just look at the one bit that is either a 0 or 1, indicating that it's a negative or a positive number. And now we add this mask to the number, and we XOR it with the mask, and this basically removes like the bit, setting it to positive. And this works exactly the same, it does exactly the same, but now you don't have any branches. Your CPU can just always do this. This is faster.
Yeah, it's substantially faster because of because the CPU can fill the pipeline better. And we'll later see this more as we go towards the really advanced optimizations. It was starting to be like filling the GPU pipeline because you can have 3 of these instructions even in parallel executed on the same CPU.
Yeah. So I was in my head working with these temperatures, and I wanted to make something that was branchless to parse this temperature. So there are maybe like you have a 1, a dot, and a 6. This is the temperature, 4 bytes. But I wanted to parse this into a single integer without any branches. And this is the code I came up with. So how does it work? Well, first is the same negative trick as before. If you look at, I included a small table, you can see there's all the numbers. They've got the second bit to set to 1, but the negative sign has the second bit set to 0, which is very handy. So in this case, I extract that single bit.
Yes, and so this is actually where in the contest, I was also spending some time looking at ASCII table. Because that's where you get these numbers from, right? So you look at the ASCII table, and then you look, is there a pattern here? And as you correctly identified there, right?
Yep.
The pattern was that,
the second bit.
We'll come back to that. The second bit for numbers. Yeah.
So the next thing I did was
I'm just trying to keep you slow here because I'm not.
Yeah. So the second thing is I wanted to know if the number has 4 bytes or 3 bytes. It can be 1, it can be 1.1 or 1.1 or minus 1.1. So this again, branchless, returns a single bit, and then I extract all the digits. In this case, I was still using a byte array with all the bytes in it. Not the way you should do it. But again, this was my first attempt of writing branchless code. And in the end, I just multiply everything together. One digit times 100, the other digit times 10. And I actually, if you see here, for one case, I subtracted the 0 character to get the actual number 0. And for the other 2, I didn't, because I noticed that these are always present. So if you subtract this and this times 10, it's actually 528. So that was a tiny optimization that I could do. And this was slightly faster. And then Mary Kitty, username, his name is? Kwan. He entered the chat, he submitted something, and I literally fell from my chair, because this was his code to parse the temperature. And I now have to explain this to you. Took me a while even to get it, but I think I'm able to do it. So what he's doing, he's reading this entire, all these bytes that represent the number as a single long value. Again, this is already way faster than what I did, because I was reading those bytes individually. So if we do this, for example, the temperature in this case is minus 18.3, and it is some junk, because you will always read some junk that you don't need. But we can filter that out. So again, this is flipped in this case. The first thing he does is he looks at those 2 bytes we mentioned before, and he wants to determine where this dot is. Like, this dot can be in 3 possible positions. It can be in this position, can be if it's 1.1, it's in the first position. If it's 1.1, it's in the second position. If it's minus 1.1, it's in the last position. So it can be in either three of these bits. And he just singles out these bits.
Yeah, so because the structure of the input data is that, well, you always have one number after the comma, which is great. But then before the comma, you either have 1 digit, 2 digits, 1 digit and a minus, or 2 digits and a minus.
Yep.
And from this structure, you know that there's only 3 cases of where the dot could be. And based on these 3 cases, now you need to come up with this crazy
So what he does
multiplier.
What he does here is he does the number of trailing zeros again, which is one machine instruction, and you get either 12, 20, or 28. Those are the positions that it can be in. What he also does is basically the same thing as we saw with the absolute value trick. We shift the number 95 places one way, and then 63 places the other way, which basically takes the sign bit and it smears it out over the entire long value. So it's either all zeros when it's a positive number, or all ones when it's a negative number. Cool trick. Now we take this number, this either 12, 20, or 28, and we turn it into 16, 8, or 0, because that's the number of spaces that we need to shift. Again, you could do some calculations, but this is just one XOR operation, and magically it turns these 3 numbers into the actual 3 numbers we need. If it has a minus, we need to mask this bit out. So in this case, if it's a minus, it was all ones, and if we end it together with FF, which is the first byte, we create a mask, either 0 or we mask it out. Now, we are only interested in these bits of the bytes, because those represent the actual numbers. You can see for character 0, if you look at those 4 bytes, it's 0. And if you look at character 1, if you look at those 4 bytes, it's actually 1. So very handy. If you use this 0f, 00f, 0f, you only get the parts that we actually need. And the rest is filtered out, and is using this minus filter to also filter out the minus if it is in the way. And we are very close now. So we end up with one number, and if you look at this format, the UU, that's where the units are. TT is where the tens are, HH is where the hundreds are. So in the case of minus 18.3, we want to end up with one integer value, which is 183, but we're not there yet. We've got this weird number, and if you look at it in hex, it's actually 0x030008. We're close, not quite there yet. Turns out, if you take this number and you multiply it by 1, you get the same number. But if you multiply it by 1000L, you basically shift the number. And if you multiply it with that other number, you can shift it even further. And it's possible, if you multiply those 3 numbers, to align the numbers that we actually want. Turns out, if you multiply by these 3 numbers added together, the result is actually these 3 numbers added together. So 3, 8, and 1 added together is 0C, which is 12. So we're close now. We're close. We're turning these individual bytes into something combined together, and we're close, but we're not quite there yet. The only thing we need to do is actually shift and also multiply one of the things by 10, and also multiply one other thing by 100. And if you make this into one magic multiplier, which is on top, turns out the result that you get in that specific spot is B7, which is 183, which is the number we are looking for. And for some odd reason, the way these bytes were situated in the number, you don't get any overlap. Because just as easily, you could have gotten some overlap, and this trick would not work. But in this case, per chance, it works. And you can actually go from individual bytes to getting this one integer value, 183. The only thing left is to reapply the sign value, which we've already gotten. So basically the same thing as the absolute value that we saw earlier. And for some reason, this works. without any branches, you can turn a string of bytes into the integer value of this thing, and
Yes, it works, and it's substantially faster.
it's really fast. It's really fast.
Yeah, and now one reason why it's so much faster is that most of the operations, you see a lot of operations here, there's a lot of shifting and XORing going on, but most of the operations here are very, of this kind, where the processor can actually do three of them in one cycle. So the only heavyweight operation in there is the multiplication on the bottom, which you unfortunately need. But other than that, it's super fast to move through that. And this is the optimal sequence. And I was at the end of, towards the end of the contest, I was at some point trying to save some machine instructions in this sequence, and I couldn't find a better sequence. So
Yep.
it was really awesome.
I saw this and I
yeah.
was like, this guy is a genius.
Yeah,
And
yeah,
you
absolutely.
saw it.
I saw it. I also saw this guy's a genius. I don't want to compete with him. So I invited him to join the team.
And how he works for his team.
Now he also works in Graal team. That's true. But even for the contest, he was joining because on the other parts, like his solution was slower. But if you now combined his version of the temperature read, it was giving 25%, the SWAR scanning and the temperature read, yeah. And Kwan was then joining the solution as a co-competitor, and we're very happy to have him now on the GraalVM team, and he's helping optimize the Graal vector optimizations as we speak. So Kwan is awesome, and I think you will all soon have faster Java programs because of Kwan. Not just for this specific case, but because of his contributions to the Graal optimizer. Yeah, no, that was beyond my.
Yeah, I couldn't come up with that.
Yeah, but so and this is kind of very problem specific. But on the other hand, some of the bit shifting, like the shifting, XORing, and counting, can also be more generally applied to your problem. Maybe if you have a data parsing problem, So now. The next thing, of course, is with such a contest is, well, as you get towards the more optimal solution, you start to really think about the constraints of the problem and how you can specialize for the dataset distribution without breaking the rules. And Gunnar made certain specific rules. He said, yes, the program needs to work with any dataset, and the program must not have the city names be baked into the program. Because with native image, of course, you could, in theory, even bake the whole city names into the native image itself as a starting point, which would make things faster.
Actually, there was a release of the GraalVM during the contest, and you immediately updated the version, and I was like, I'm pretty sure he just put the city names in the Graal itself.
That was a bug fix.
That's what he keeps saying. But after that, he overtook me and never looked back.
Yeah, you know this strange version name, Graal 2021.3.brc, right?
Yeah.
It's you should check that out. Yeah, but so you specialize for the dataset distribution, and there was some people doing data analysis on data sets, and also during the contest, many participants would analyze that, because one of the most important aspects of the contest was how large are these city names. Because as you parse the rows, you're always parsing these names and then comparing them against the hash map entries, right? And it was interesting that the city names were distributed as shown on the chart here, which means most of the city names, like almost all of them, are below 16 bytes, which happens to be 2 longs, and 50% of them are even below just 8 bytes, because it's very small city names. So therefore, in the solution, I then tried to specialize on these 2 cases. Because now we knew that, okay, 98% of the cases, the city fits in 2 longs, and only in 2% of the cases, it's the corner case thing. And in 50% of the cases, it fits just in 1 long. And that's why the result data structure that I was starting to use is I was starting to inline into the data structure. I was starting to inline the first 16 bytes of the city name into the data structure. So what I did here is a manual object inlining. Unfortunately, virtual machines and Java virtual machines currently are not very good at object inlining, which is a technique where you have two objects and you inline the content of one into the other. So what the object A would point to object B, typically, but what you can try to do is just inline the contents of object B into object A, right? And this can be, of course, much faster, because one issue with this object-oriented type of programming is you always have the pointer hops, which are a memory location away, and which is an indirection. So you will do this manual object inlining. Now, one reason why currently virtual machines for Java are not very good at this is that when you do this object inlining, you lose identity. And at the moment, at least, Java is very strong on needing identity for almost any object. But there is some hope that with Valhalla finally having some influence on Java and Java spec, that we will get some relaxation with respect to object identity, and then this type of optimizations could be done more generally. But we are doing these optimizations also in the Graal compiler, which is of course written in all Java, and there also sometimes we would manually inline the contents of an object into the main object, and this is why here I'm inlining the first two fields here, last name long and second last name long, would be the first 8 or 16 bytes of the city, and it's inlined into that result object. And the other thing, of course, is that when you now scan through this whole, you scan through this, through the city names, again, you can specialize for the two cases that matter to you, which is this case of 8 bytes and the case of 16 bytes. And then the case of more than 16 bytes is a corner case that you don't need to optimize anymore, and you can put the code for that somewhere down there and don't worry about it. But because then for the 8 length case, I can just
you only
one
compare
comparison.
With,
it's one comparison. It's one field access comparison, actually. Like if you look at the,
I'm not sure where it is.
the mouse is somewhere lost. Okay, no, but so if you look at the existing result that last name long equals word, you're looking for the mouse.
I'm not tall enough.
Right. But maybe we can make this now a little bit more codey. Yeah, no, let's not show this one yet. This is. Can we need to make it a little bit bigger? Can we zoom the whole thing, or
we can?
All right, that's good. Right. Okay. Now I have a mouse. That's good. Yeah. So what you will see here is essentially I'm specializing for the 8 length case, and then looking up this and comparing it as just a normal field compare in Java, and then in the else case I'm specializing for the 2 field case, which is just checking 2 Java fields here. And in this way, I could specialize on those 2 cases, which were 98% of the cases of city names, and this was another relatively substantial speed up. And so it was a 7% speed up to specialize on those 2 cases. And again here, and this is something that often happens when you have any type of performance problem, the data set or the input data is very skewed in the sense that 98% of the cases are like this and only 2% of the cases are different. And then in such a scenario, you can really focus on the 8 and 16 byte cases.
Yeah, and it's funny because Gunnar's data set only had 100 different city names. Like you said, people were optimizing for this specific format. There were also people who had created their own data sets which had city names with much longer names, randomly picked, and up to maybe 1,000 different city names. And there were also benchmarks for that running. And it's funny to see your code was really bad at those cases because it's optimized for specifically for this contest. And other solutions were more general, slower in the normal case, but relatively fast in the other case.
Yeah, absolutely. And this was
general.
kind of a trade-off that one has to make because, yeah, there was a case of 10,000 city names.
Yep.
And then for 10,000 city names, you need a larger hash table.
You get more collisions.
Your collision function needs to be more sophisticated. Whereas
Right,
here, in this case, right, one important thing on this whole data set was that while we had to be in theory supporting any city, we knew the likely set of cities. And so you could make the perfect hash function work. So you had a relatively simple hash function that guaranteed you no collisions on the example data set.
Yeah, but we could not rely on that. So even if you wrote a perfect hash function, Gunnar mandated that you should still always check the value. Like
Right.
you can't skip this.
Right, you can skip the jack, but the check could be in a very slow pass. So you don't need to optimize it anymore.
Exactly.
So that was the compromise then for the rules of the contest. Yeah.
Yep. I'm a huge Formula One fan, and this is Sir Jackie Stewart, and he said, well, you don't have to be an engineer to be a racing driver, but you got to have some mechanical sympathy. And mechanical sympathy is the term that basically we're using here. So if you understand the platform you're working with, and if you understand how a CPU works, how instructions work, you have an advantage. Same thing for Formula One. You don't have to be able to build the entire car, but you have to understand what is happening underneath. What is happening in the suspension, what is happening aerodynamically. This helps you tweak and optimize. This is just one example of what a CPU looks like. You can see there's the little L1 core. This is the memory for each and every core. It's really small, but it's really fast. It's located next to the core, so it doesn't have to travel a lot. And this is by far the fastest memory, but it's small. Then you have the L2 caches. These can be shared, but in this case, every core has its own L2 cache. And there's also a shared L3 cache, which is, again, larger, but slower. And as you can see here, this is just an example of the differences in times it takes if you read data from an L1 cache, very fast, L2 cache slower, etc., until you get into main memory in disk drive, which is really slow. So you want to avoid this as much as possible. If you read something, you want ideally to have it stored in your L1 cache already. That's by far the fastest. So how do you optimize for this? And this comes into optimizing for this problem multiple times. And this also helps, for example, if you divide the file into 8 parts, each processor has their own thing and they're always reading the next value from there. So if this gets loaded into the L1 cache, that's perfect because all the bytes there are processed by that processor. In the initial case where we read the entire file and we were processing that in parallel, it could be that the first 10 bytes were processed by the first processor, the next 10 bytes on a different processor. So that means that data is being loaded into 2 separate L1 caches, which is a shame. So that's also something you need to keep in mind. That's happening in the background. So we can read a file using mmap. We can find and read the city names using SWAR. We can compare them using long values. We can branchlessly parse these temperatures. But we also need to store this data. We need to store the city names we found. We need to store the temperatures that we've already read and the sun that we have so that we can calculate the average temperature. And initially, you as well, and me as well, we were using a map because a map data structure works perfectly for this. So we were using the Java hash map. So this is a very simple back-to-school example. How does a hash map work? Suppose we have a string, Antwerp, and we have some temperature. We first calculate some hash code. Usually, we just take the string and we call .hashcode. This is just a number. And in this case, the hash code has size 8. So we do this big number modulo 8, and we put our thing in position 3. Perfect. Next time we get Antwerp again. Oh, didn't update the slides after DevOps UK. Next time we get Antwerp again, we can just do the same thing, same hash code, modulo 3, and we end up in the same spot, and we can update the temperature right there. What happens if we have a different city, Rotterdam, different hash code, but our hash code is very small, so we have a hash collision because it also wants to write in 3. The Java implementation of HashMap basically starts to build a tree structure. So when you get to point number 3, you say, well, is it Antwerp? No. Then we traverse the tree and we go to the next and the next and the next. So this is a nested tree structure, and it works. And if it becomes too crowded, these buckets become too full, it actually will resize the hash map and it will recalculate everything. And that's not something we want. So the first optimization you can do is look at the data set and again determine, well, there's 100 city names. So if we make it 120, it should be big enough and it should not resize. So that doesn't take any time. But we can do faster.
Also to notice that the hash map implementation in the JDK, it is always, there's an array in there, but every entry is in a separate object, which is a hash map.node in a class.
Yep.
And so you already have one indirection. And in our case here, and the reason is that the node of a hash map has a value and a key, both of it. But in our case, we want the value and the key to be just one object. And that makes a much simpler hash map implementation possible, where you just have an array of keys.
Yep. So what I did is I went to ChatGPT and I said, well, what else can I do? Like, I don't want to use the hash map that is provided by Java. I want something else. And basically told me, well, make a forward probing. Make your own hash map and make it forward probing. I had no idea what forward probing is. It just means use the next one. So if you have a hash collision, so we try to insert Rotterdam, but Antwerp is already at the spot. Just put it in the next empty spot. And this is surprisingly simple, and it works very well. And if you now look at the entire implementation of my map, which is really simple. So first, we have this hash number. I end it together with the size of the table because it's a power of 2. Normally you would need a modular operation, but that's really slow. End it together faster. And while true, so we find an empty spot. We make the table large enough that we will always find an empty spot. Now we get the entry. If this entry is null, then we insert this entry. And actually, I was doing something that's called a flyweight pattern here. I was basically, the objects I'm storing are not real objects. I'm just storing a byte array, and I'm using unsafe to.
I have to. Yes. So this was. Yeah, I felt already guilty by introducing unsafe a little bit, and then I saw some participants in the heat of the moment. They didn't go unsafe, they got full unsafe.
Yep, no more objects.
So they flattened the whole map implementation into, and I mean, hopefully, Valhalla in Java will soon actually allow us this kind of arrays because what you want is again, this kind of object inlining. You want to inline the hash map entries. Yeah.
You don't want to have any object headers and other stuff.
Yeah, no indirection. The indirection is the main problem, right? Yeah. Because otherwise you go to the hash table array and then you need to go a hop to the object, right? And therefore some participants were flattening out everything. And I refused to do that. And surprisingly enough, it was not such a big difference. Yep. Because the advantage that you have if you have actually the hash table pointing then to objects is that the objects themselves are closer together in memory. Because the objects will be the objects that are allocated for me, like the result objects, they will be all in memory very consecutively, Whereas if you inline these objects into your hash table array, they will be a little bit more scattered out. And this additional scattering of object seems to be a negative, and that's a similar negative as the interaction that in my implementation I'm taking, where I'm going from the hash map array to an actual Java object. So this code really doesn't look like Java that much anymore.
Nah.
But thankfully, even Java with a little bit of smaller tricks can like get there.
I was actually jealous because your solution was faster and it looked way nicer. So back to the hash table. If it wasn't there, we can just insert it. If there is something there, we need to check if it is actually the thing that we are looking for. So we need to do the matching, basically the code you showed earlier. And I need to update my entry again. You would not like this, but I was doing everything in memory. And if it wasn't the entry we're looking for, just go to the next one. Like, it's that simple. Just index +1, try that one.
Yes, you can go to the next one. Another trick here is to go to the, not +1, but you can also do plus a larger number, like +31 or +37.
Yep.
Which is a tiny smidget better in case you have collisions, because you're less likely to be skewed. But in general, it's really surprising easy to implement your own hash table this way, and it's substantially faster with substantially lower memory than what you would get from Java util hashmap.
Yep. The spawn trick.
Oh yeah. No, now it's getting. Now we're starting to get low level. Okay. So yeah, we will have to become Linux kernel developers now. So let's see. Now, I was starting benchmarking my solution, and I was starting to use Perf, which is a Linux tool for analyzing the performance of a process. And thankfully, with native image, Perf works really, really well. So it gives you very detailed information about your process. The standard command line you would use is perf record, and then you say globally, and then you say that you want to get the first 999 samples, and then you use perf script to get a file that you can then put into the online Firefox profiler. Now, one thing here is perf only works on Linux, and in order to get kernel profiling, you need to set certain flags. The flag is called something paranoid. I don't remember, but if you search perf paranoid flag, you will get to some obscure Stack Overflow page that tells you how to set it. So I set the flags, and I'm profiling with perf, and I'm like loading this into the Firefox profiler, and we have this here online.
That's pretty good.
Yeah, we can make it. Is
No,
it
it's
big
good enough. I think
big enough?
you can read it, right?
Right,
Yep.
right. Let's do one more higher. Okay. So I'm looking at this, and you see, this is what the output looked like. It's a typical like output of profiling information. What's happening here is that the yellow parts is where the program runs, and the orange parts is where the operating system runs. This is where the kernel is running, and you see the threads are doing their work, and sometimes the kernel is a little active because the kernel needs to load some pages. So it gives you a real full view of a Java app, right? And then I'm scrolling through this whole profile. Look if I see anything bad, if I see anything wrong, right? And and then I'm like, what the fuck? Like, what is this? And
So that's like 20% of the time it's waiting for something.
because it was always so weird to me. Like, I mean, why does the profiles? Why do all the threads only work until 500 milliseconds? But my process timing shows 600 milliseconds. Like, how is this possible? So, and then you look into these things, and you look at this code. And I'm not a Linux kernel expert. Maybe you have one in the room, but it's something about unmap page range, supping. I guess what's happening here is that when we, at the end of the process, the Linux kernel, for security reasons, is unmapping the whole file, this 13 gigabyte file that is the contest file, and supping the memory contents such that the memory is cleared out. And it does so in a surprisingly single-threaded manner. And this meant that when you ran this process, you were doing all this work in Java here, nicely parallel, and then you wait until the Linux kernel in a single thread is kind of unmapping this stuff, right? I mean, they always say Java is slow and C is fast, right? I mean, in this case, it's definitely not a thing, right? But yeah, so this is a problem, and it shows that on this computer, at least on the solution, it's 100 milliseconds, like 16% speed up, if we can get rid of that. And I tried different approaches, trying to do the map one file, like one segment per thread, like have multiple mappings, but none of them seem to work. It's always seemed to be the case that the Linux kernel takes out the lock on the overall process when doing this unmapping, right? So kind of yeah, so this is a problem. So what do we do, right? I mean, I was going on Twitter asking other Linux experts and so on, and I was like considering to submit a patch to the Linux kernel, but like then I saw this, right? So what would happen when I submit a patch to the Linux kernel, right? Yeah, I didn't want to go there.
Get it approved within the contest. That's hard.
That's right. And getting it approved within the contest size also seems hard, right? And then Gunnar would have to update the Linux and patch it, right? So
yeah.
So it doesn't work. So that's why then one of the Graal team members, Alfonso, he has actually, by the way, a talk on I think tomorrow on AI stuff. He's here at the conference. Alfonso was coming to me and said like, "Hey, Thomas, I have a trick." And I said, yes, tell me all your tricks. And the trick is that you will now, if you go to the source code here of the solution number 7. So the trick is make it bigger, right? The trick is that we are now. So hyperfine is just measuring the time of the process that is producing the result. And what we're doing now is the process that's producing the result is spawning a second process that is calculating the result. And that second process is the process that is mapping and unmapping the file. But the first process, once it receives the result from the second process, just finishes, and hyperfine will take this as the result of the time on that process, and it will not count that in the background the second process is finishing the unmapping. Sounds good to me. So but of course, yeah, as we can hear from the laughter in the room, I was fearing that I could run into some problems with the auditors. There's always these issues with tests, and if you specialize too much on tests, right? So I decided to put some pressure on Gunnar on Twitter to ask him if this is legit, and thankfully. Thankfully, he was accepting this, but it was, of course, again, with a lot of other tricks, it was then applied to all of the other solutions as well, so everybody was allowed to use the trick. And in this way, we could get the timings down another 10-15%, right? So this is, again, that's this code that I showed on the IDE, where you have in the main method. It's the same image actually that runs the worker, like the worker process and the original process, and you just check, you just spawn the worker with with minus worker as on the command line, and then the second process knows, okay, I'm not supposed to spawn another process, I'm supposed to do the work and give back, right? Now, one concern I had when I submitted this PR to Gunnar's main repo is that if somebody makes a mistake in that code and, for example, is not correctly specifying this minus worker flag, like if you make a little typo and on the line
Now you've created an infinite loop.
yeah, you will spawn a lot of processes and bring down the benchmark machine. So it was definitely something that you needed to be careful to put exactly that snippet.
I was actually surprised that he approved this. I thought it would say, well, just deal with it.
Well,
it's
I mean,
everybody's problem.
why should Java look slow because of the Linux kernel? I mean, I think for the benefit of everybody in the community, I think it was a good thing. But yeah, no, but and this trick is actually used in some scenarios in practice as well. I was googling later if anybody else had problems with this type of situation, and it is used in practice even by some people. But now one thing that still happened here is now, and you could see this in the hyperfine output, is that because hyperfine is just running the example many times after each other, like 5 times after each other, and you could see after we applied this trick you could see in the output always that the first run was always the fastest, because once you started the second run, you had a certain overlap with the work that still had to be done for the first run. Because the unmapping was still going up on in parallel in the operating system, and the second run was already starting. But that effect was relatively small, and the performance benefit was quite substantial, right? Now, the performance benefit, of course, was best on native image, because on hotspot, if you use regular hotspot, the trick didn't work because the startup time is so slow that starting these 2 processes takes too long, right? But that's why the hotspot solutions, the cheat solutions, would later use a command line utility from Linux to spawn that subprocess, such that they are not disadvantaged because of that trick, right? But in general, the takeaway from some of this is that you should definitely consider looking at the performance also via Perf, because if you only look at the performance with Java level tools like Java Flight Recorder, it will never show you this problem, like ever, because from the perspective of Java, this kernel doesn't exist. So therefore, having here the lower level profiling tools can sometimes get you an additional insight to where your application is actually spending time and how much time is spent in kernel code or operating system code or some other part of the system that is not your Java while loop, right?
Yep.
And I think this is shown here, and it's very easy with native image specifically. You just run the perf command and you're good.
This is also the moment that I kind of lost the contest, because for one, I had an M2 MacBook, which internally works very different from a machine that was, Gunnar was running this machine on a cloud server, and this was obviously a big Linux cloud machine somewhere. And the architecture of that machine is really different from an M2 MacBook. And like you said, like, what do you say about memory? Like the memory reads,
the
writes?
memory bandwidth is very good on the MacBook, and on the Intel i9s, the Intel i9 was very close to the benchmark machine, which was an AMD Ryzen, I think. But they had a much less memory bandwidth, whereas the MacBook has a better memory bandwidth. And when I looked at your solution, Roy, it was like, oh, he accesses memory a lot and writes even to memory a lot. And for his solution on this computer, it was like
because
not a problem.
On my machine, I had the fastest code.
Right.
Like your code was slower on my machine,
Right.
And I was optimizing on my machine. But that's not the machine that the contest is running.
Right.
And one other thing, I could not run Perf because I'm on OS X. On an M2 MacBook, I can't run Perf. Actually, it turns out I had an old MacBook, which was an x86 MacBook, that could run Perf.
Right.
And that was actually much closer to the machine that was like internally, the things that
also
worked.
because of the processor is
Exactly.
much closer. Much
Exactly.
closer.
So halfway through, or not even halfway, in the last 2 weeks, I switched this laptop out. Sorry, it's perfectly good laptop, but I was using my older MacBook because things correlated a little bit better. But yeah, in the end, if you wanted to win this contest, I think you either needed to work with compilers, or you need to rent an actual machine, like the same machine that Gunnar was running to benchmark everything, and test on that machine.
Testing on the actual machine would have been even the better thing.
Yeah. So that means renting out stuff, and I'm Dutch, so I'm cheap.
I mean, I also didn't want to go there, but yeah, I mean, an x86 was close enough, an x86 on Linux, but it's true that we are getting now towards like really as we are getting the last milliseconds of the timings, and it's getting very.
And it was surprising to me that it made such a big difference. Like, how could it be that my program is really by far the fastest on my M2 MacBook, but not in the benchmark? And every time I made improvements and I made it better on my machine, and I submitted it, and Gunnar was running, and it was slower. And I was like, how? It's almost a second faster on my machine now. How can it be slower on your stupid cloud machine?
But the machines are different, and in this scenario, it's the memory bandwidth. So your solution was saving on instructions, but it was using the fast memory bandwidth a lot, but when you submitted it to the cloud machine, there the memory bandwidth became the bottleneck, and So the other thing, because I was already opening this with the Firefox profiler and so on and so forth, right? And so the second thing, after I fixed this problem, like this is now the new profile here. If you look now here, this is after this is with the unmapping problem fixed. So now you can see, okay, we don't have the problem anymore with the Linux kernel in the end, but there's still an issue, and the issue is that when you look at the very end here, some workers are finishing faster than others. Like this guy is already finished at 450 milliseconds, and then it takes another 5 milliseconds where this guy does nothing, right? And so this is where you could see that the split in terms of workers, and on the target benchmark machine, it was actually only 8 workers. It was a problem that, like, if they're not evenly executing, that so one would finish faster than the other, and you don't fully use the machine to the end. Right?
You spawn 8 threads, you divide this entire file into 8 equal parts, but one might be faster than the other, and then the others are waiting for the final one to basically finish, right? So it could be something like this. So one would be finished much sooner than the others. So there's one thing you can do to actually improve on this, and that's using even smaller segments. So we're not dividing this entire file into 8 parts. We're just using like 2 megabyte chunks, and we're using an atomic long as a pointer in the actual file to the actual memory. And these 8 threads, they're constantly reading the next 2 megabytes of data, one after another. And this atomic long, because it's atomic, multiple threads can update it and basically assign their own part of it. So this works much better because you don't have the problem that eventually, when everything's finished, you're still waiting for the final one to finish because the chunks are really small. Second thing this does is, in the big scheme of things, on the operating system, on the memory mapped side, you're now processing this file from start to end with 8 processes at a time, but in 2 megabyte chunks. And these 2 megabyte chunks, they correlate really nicely with the the L2 and the L1 caches. So you still load a part into the L2 and L1 cache, which this particular processor is going to process. But one step beneath that, this entire 13 gigabyte file, we're still processing it from the start to the end. So the thing that's loaded in the L3 cache is still the beginning of the file, and then the next bit of the file, and then the next bit. So we're not randomly at 8 spots reading this entire file. So this was another big speed up, I think. Well, couple of percentages.
Well, I mean, at this stage, we are fighting for every percentage.
Yeah.
I think it was 7-8%. And yeah, it was interesting that the segment size that's used per thread was 2 megabytes. And I experimented with different sizes, and 2 megabytes was always the optimal. Seemed to be on my machine, and I think also on the benchmark machine, which is, as you said, corresponds to this L2 cache sizes. And yeah, and it's very interesting as well that the way you program this in Java is actually quite elegant with this atomic long counter object. So you take the atomic long counter.
Who here doesn't know what an atomic long is? Oh, some people. We should explain what an atomic long is.
All right.
Basically, it's a long value. Making it atomic means that if you do an operation on it, it's guaranteed that nobody else is doing an operation at the same time. So your operation is unique.
Right, exactly. So we are creating this atomic long object. And this is a pattern actually, even in regular code, can sometimes be useful. If we go up here, where do I create this object? Yeah. Here I just create an atomic long cursor object. It's a global object. It only exists once. It exists once for the whole program. And then
multiple threads are using that same atomic long.
Yeah, every thread is using the same object. And then in the parse loop, the important part is here, where every thread is now concurrently calling the add and get method.
Yeah, and there's nothing between adding and getting. So the result you get, this operation is atomic, like it's a unique thing. Adding and getting the value, and no other thread will add at the same time. So if you're using regular long, you would maybe get the value, and then another thread also gets the same value, and then you add to it, and then things break because you did the
because they
dirty
would
read.
overlap. Yeah, both threads will get the same piece of work. But with this add and get atomic here on the atomic long object, we're guaranteed that every segment is given only uniquely to one thread. And if two threads would be very close together and both of them would kind of call this add and get, that one of the threads is going to win first, and the other one will get the next segment. And this pattern is, again, this is super elegant here in Java to write this. I was actually surprised how fast it is to go here from the coarse-grained processing of segments to the fine-grained one with just this pattern of global atomic long object and then add and get for work scaling.
Yeah, I think it's mostly like the L2 cache and even the L3 cache. The fact that all the processors are reading from the same part of memory. Yep.
Yeah. It also helps the Linux mapping, the Linux kernel code that is loading the file from disk to make sure, because otherwise it could be confused by which ports we're currently processing. And in this way, we are now really always locally moving through the whole 13 gigabyte file, and we are guaranteed to be finished all at the same time.
Or as close as possible, within 2 megabytes. So
yeah, within 2 megabytes, that's for the size of the file that's neglectable. Exactly. Yeah, so this was a very important optimization here.
This was the last couple of days of the contest that people started doing this.
Yeah, so it was getting exactly, crazier and crazier. And the next,
don't repeat yourself. That's what everybody is always telling you. Like, keep your code clean.
Yeah, so the next fun refactoring of the code, which got another 5% or so. But as we said, at this stage, we are fighting for the milliseconds. Everybody wants to win. So it was to process multiple, like every thread is processing always row after row, right? but now we want within one thread process multiple rows at the same time. And so I'm finding the delimiter for the first row, finding the delimiter for the second row, finding the delimiter for the third row, and then the same thread is parsing, and the same thread is parsing the temperature, and the thread is doing it always.
Well, why 3? Why 3
Why
times?
3? That was interesting because I tried 4 and 2 and both were slower.
Science.
So, as you can see, at this stage, some trial and error is involved, right? Now, yeah, so this is how the code looks like, and this is why I said also this scanner object, having this scanner object is very handy, because if you not have a nice code now and have the scanner objects, you will be in trouble. And yeah, so and then in the end, like this is the three processing steps, right? But you need then in the end, you need to still process kind of the rest, because they could be uneven. There could be a problem because you have a segment, right? And you divide it into 3 parts, and you start processing those 3 parts in parallel in the same thread. I mean, it's not in parallel, right? It's like at the same time in the same thread, right? Then you have the problem that they could be unevenly distributed, and so you need in the end get the rest going, right? Now, why is this faster? I mean, it's not a lot faster. To be fair, it's only, I think, 5-6% faster. And the reason is that the processor itself, every CPU, I mean, the processor is parallel, of course, has multiple CPUs. In our case, for the benchmark machine, it was 8. On my machine, it's 32 CPUs. So it has multiple CPUs, but every CPU has multiple processing units for doing certain computations. And depending on CPU models, there could be more or less for one computation. So a CPU could have like 3 multipliers or 2 multipliers. And the thing is, the CPU, when it sees the machine code, it tries to fill up the pipeline. And duplicating here the code made it more likely that the machine can fill up the pipeline in full, so that always all of the processing units of one CPU doing some work that is useful. And the benefits of that outweigh the costs in this case of this additional, because you have some costs of this additional segmenting, right? And you have also costs in terms of, the thing is this, if you overdo it, if you do now 4 or 5 or 6 times in parallel, you run into the problem that you run out of registers to hold your values. Because you still want your intermediate values to be held in registers and not be spilled on the stack, because that will be much slower, right? So you wanna parallelize enough that you can use more of the parallel units of the CPU, but you don't want to have so much parallelization here of the code that you're running out of registers. And that's why I think 3 is good here, and it's better than 2, and it seems worse than 4. I tried all versions. And yeah, as I said, the code looks funky. You will have to bring it through the code review of your company first. They might ask some questions. But it is getting indeed faster. Yeah, so as you could see, the the amount of the benefits here is only 4%. It's not huge, and it's both this processing in 2 megabyte chunks, and it's the copy and pasting of the code. But 4%, we take 4%. The contest is heating up, right? It's starting to get January 31st, so we got to do everything, and everything includes now hunting for machine code instructions that we can save. Because I talked about Perf a little bit, and let's talk a little bit more in detail on the Perf stats here. And so this is the output that you get when you do Perf stat on running the program at this point. The output is a little complicated.
What do we see?
Yeah, what do we see, right? I need, I think I need a mouse now, so maybe let's go into this phase. Right. Oops. All right. Can I get that off? Okay, good. Okay, so now I have a mouse. You see my mouse? Yeah, okay. So one interesting thing here is, for example, it shows the number of page faults. Because we have memory mapping the file, we are having 220,000 page faults when running the application. But that's natural, and it shows that whenever the operating system gets such a page fault, it's already mapping in multiple additional pages.
What is a page fault?
A page fault is when you're accessing a piece of memory on the file that is not yet you're accessing a portion of the file that's not yet loaded in memory, right? And so then the operating system needs to go and fetch that portion. And it has a heuristic to fetch one page, at least, but it also fetches more than one, because otherwise it would have more page faults here. I calculated this before, and it seems to be the case that it fetches about 40, 50 pages at the same time. A page is typically on Linux 4 kilobytes of data. Now, it shows us the CPU cycles that the program is running on. And because this machine has Atom cores and performance cores, modern Intel machines have different types of cores. Some are a little bit faster than others. We get both of them together. My machine here has 16 Atom cores and 8 performance cores. And we see the number of cycles that this program goes through. The cycles is a good indicator for how long the program takes, because the cycles
It's a clock cycle, right?
it's a clock cycle, exactly. It's a clock cycle. It's a clock cycle, and here we see how many gigahertz we're currently running here on the machine, whether it's overclocking, underclocking, whatever. But this is the number of cycles it takes, which also means during performance measurements, it's better to look at the cycles taken than at the task clock or something else around this, because the cycles should be a good indicator for how fast the program, or how much work the program has to do currently, right? And then we see the number of machine instructions that the program was going on for. And this shows how many machine instructions the machine was executing when running the program. And as you can already see, we are actually executing more instructions than cycles. So in one clock cycle of the processor, we are executing more than one instruction. This is what I talked about when I said the CPU processing unit has more than one
these numbers look very
computational unit to make an operation.
These numbers look very big, eh? Like it's 32 billion instructions. But that means that when we process 1 billion records, we use just 42 instructions on average per record.
Yes.
Which is really small.
Yes.
It's crazy small.
Yes, it's accurate. Exactly. Yeah, we need to, on the bottom here, I added up these numbers because you need to add up the performance and the atom cores. But it means per row at the moment, we are executing 52 billion. In total, we are executing 52 billion CPU cycles, which is 50 cycles per row. Okay, so it takes us 50 processor cycles per row to execute. And we are executing 100 billion instructions total.
In these 50 cycles, we take the data, we turn it into integer temperatures,
Yes.
we look in the hash map, we
Yes.
actually update the min and the max value,
Yeah, we check
all
the name,
in 50
yes.
cycles.
Yes, it's
which
50
is crazy.
cycles, and it's 100 machine instructions. 100 machine instructions for one, parsing the row, putting it into hash table, and making sure that the hash table has no collision, etc. Right? So this is pretty good. But of course, now we are at the phase where if we can somehow find one machine instruction somewhere to be saved, we're going to get 1% ahead, okay? Sounds good, right? So I'm, all excited to to get there. And now, what we also see here, by the way, and we'll later come to this back, is we see the number of branch misses, which seem quite high. And we'll later see this as we go to the final
version of the solution.
This is not even the final version.
Yeah, that's not the final version yet, right? Now, yeah, but this perf stats can give you a good indication. Now, perf stat on the top, on the middle right here, it tells you how many instructions per cycle you were executing here. So this is 2.2 or 1.7 instructions per cycle. This is how much the processor could fill up its own pipeline. And the higher this number, the better for you, because the more work is done in one cycle. And when you look at the perf output and you see for your program a low instruction per cycle, it means you're not efficiently using the underlying processor. And the optimization I just showed before, this like copying and pasting of the code, it made the instruction per cycle go up. Yeah, but so we are down to machine code instruction stuff, right? And now we need to look at machine code instruction things. And one good website for this, which I can also recommend, is called Compiler Explorer, but the website is godbolt.org. And in this website, you can put in a certain piece of code, C code.
That's good enough.
In this case. And then that piece of C code, it shows then on the right what machine instructions it is translated into. And the piece of machine code that I have here on the left, it is taking an index, it's multiplying it by some number 4, and it's saying +1 on it, and then it accesses an array. And on the right, we see here, okay, it's getting this index local variable. It is multiplying it by 4. Of course, it's not multiplying it because a multiplication by 4 is translated into a shift by any reasonable compiler, because you can shift it by 2 instead of multiplying by 4. It is then adding 1 to it, and then it is accessing the value. Okay, so that makes sense. It's a straightforward translation of the code into assembly. In this Compiler Explorer, we can, by the way, select a different compiler, whatever we like here. There's many different versions. And we can give compiler options. And currently we give no option, but the option we want to give here now is O3. And if we do O3 and we compile this piece of code on the left, then we see that what GCC is actually producing in terms of code, it is just one machine instruction. It is just now accessing the array at this is the RSI is the array itself, like it's accessing the array. RSI holds the array value, +1 is somehow included in the instruction, and the index holds RDI. RDI is the index value times 4, and it's also included in the instruction. And what we can see from that, and what we can learn from that, is that in the Intel addressing modes, when you access a value, it can include an addition of a constant and a multiplication of an index by a small number, 1, 2, 4, or 8.
Please don't leave a comment saying, I thought it was a Java talk. Do leave a comment, by the way.
No, it is even a Java compiler will produce this for you. Now, unfortunately, it seems to be the case for the specific pattern in the specific competition. The Graal compiler did not do the correct transformation. Therefore, I will show you the transformation I did in the source code that saved us one machine instruction. But I already filed the bug with the team, and it will be fixed.
I don't feel bad anymore why I lost.
Yeah, so this also explained again, like since the 386 architecture, you can, when you access the memory, you can have
register times scale, plus a displacement, which can be 8 bytes. If it's 8 bytes, it's better because the machine instruction gets smaller, or 32 bytes. And of course, Intel introduced this back then because it's very handy for going over arrays. Makes sense. And if we now look at this in our code here, then there's a small subtle change here that got this one machine instruction. So on the top part of the code is the old code, that is the slower code. It has this pointer that we're using to go through the file, and it's adding 1 to the pointer. It's then scanning the number, doing everything, and at the very end, it is adding to the pointer the expression there is the size of the parsed number plus 3. And instead of doing that in the code below, I am putting the +1 into the calculation of the address when I'm getting the number word, and I'm adding on the bottom +4 instead of +3. It's a small subtle change, but with this change, the Graal compiler is going to fold the +1 on the top into the address calculation, and is therefore saving one machine instruction. All right, very exciting. All right. Yes, actually, yes. So we can.
Let's switch less ops.
Let's as we are talking about compilers, let me 1 second. All right, escape. As we still have a little bit of time, we are gonna get
Yes, it's working.
a little bit deeper again. Right. So let's see what happens in the compiler here. So what I have here, this is the compiler visualization tool for the Graal compiler. Unfortunately, the font is a little bit small, but it's not the most UI-friendly tool, but it's used on a daily basis by the compiler engineers. And what you see on the left here is the Graal compiler will output you a graph for every compiler phase it is performing on the application. So on the top here, you have the initial state of the application, and on the bottom, you have the final version of the application. And what you can see on the numbers is that, well, this is 123 phases that the application goes through in terms of compiler passes. Every compiler pass will try to add some optimization, would make some change to the graph. And what you can see on the bottom right here is that when we are starting off with the compiler graph, this is the compiler graph for the main parse loop, right? So this is the main parse loop. And you can see here it has 800 nodes, which is a lot of compiler nodes, but it's quite a lot. And then after we inline everything, it has already 3,000 nodes. So there's already 3,000 compiler nodes into the main loop after you inlined everything. A compiler node represents typically one operation. So to show you this here we have a compiler node, for example, that is an integer test with a constant. Then we have here, for example, a compiler node that is a AND, a compiler node that is a NOT, a plus, right? So one operation in your Java program would typically correspond to one compiler node. A compiler node can also be control flow, like here you have an if, for example. And so you have essentially here at this stage, you have this 3,000 nodes. And if you go to the bottom of this, after the compiler is done with all of its optimizations, it's 7,400, 500 nodes, right? So it typically does duplication of nodes, lowering of nodes, and so on and so forth. And we can see here some of what you see here on the screen, but is actually one of these like SWAR testing code that Roy was showing before, right? And because of course, if you look at the whole graph, you will never be able to look at 10,000 nodes at the same time. But that's why when working with the code and working in terms of like how to optimize the code, one would focus on certain set of nodes. And you see here, okay, we're reading here an off-heap location. We are XORing this value with a huge constant, which is probably one of these patterns. And this is how we then can look through the program and understand what transformations the compiler would have done, is doing with the program as it goes down to machine code. So yeah, this is just to give you a small glimpse on what is happening between your program's Java bytecodes and the lower parts of the compiler. Now the low tier of the compiler is very close to machine code, but it's not yet full machine code because there is no register allocation yet done, but it's almost a one-to-one translation from there to the final machine code. So yeah, I mean, this is only interesting in certain very special cases, but therefore I said we're looking to some of the main things we would do as compiler constructors when we look at such a graph is like, oh, let's see if there's an invoke left, for example, right? And we see, okay, there is still some invokes apparently left, but if you look at the invokes here, none of them seem probably important. Like we have some exception invoke or some invoke that's on a slow pass, but the fast pass is fast, right? And we can check if there is an allocation left here. So this is a very detailed tool and needs very special knowledge to work with. However, you can get it. It's downloadable for free, and everybody can try this who is interested in that. But in order to make some of the information in the tool available to end users,
What is the input? If you download the tool, what is the input? What do you put in?
so there is flags you put on Graal, and then it will automatically get the graphs to the tool that is running locally with you. We can, I think we have it here somewhere. It's this is the general one. Yeah, so there is actually a prepare. No, it's the prepare. Yeah, here. So in the prepare, there is some flags you can put when you create a native image, but you have to put a method filter. So you're filtering on certain specific methods, and then you're printing the graph to network, and then you're dumping on a certain level. The higher the level, the more detailed the dumping becomes. But if you create a native image and you put these three commands, it will move the graphs to your local graph visualizer installation. But it's currently very expert level, but we are hoping, because one of the things we want to get to is where some of this information, the higher level information, is also available to anybody and more easily accessible, because it can be interesting to understand, okay, what transformation was actually done by your compiler here. All right.
Yep.
So let's head to the final. Version. Yeah, we're almost done, guys. I hope you're still feeling.
The final version.
You're still feeling good.
We skipped the break because we want to.
Yeah, but you can feel now a little bit also how I was feeling after a very interesting month of January. Lots of fun conversations with Roy and others. Having a lot of new friends. Also learning a lot of new things about the Linux kernel and other things which I didn't know before the contest. And but I'm sitting there on the last evening, and I'm like, okay, like my solution currently seems to be, or our solution seems to be the first on the contest, and I'm just chilling and hoping nothing, no other random submission pops out. And I'm refreshing the page of the contest of the 1BRC, and suddenly, boom, like one of the solutions that was not on the radar to be the best solution at all was like number one. And I'm like, how is that possible? Like I was watching all the solutions. I was like, what did I miss? What did I miss? And it was number one, not like by a substantial amount. And I was like, oh my God, what did I miss in this whole like contest as I optimized smaller and smaller things? As you can see, also going down the line, I'm, -7%, -7%, -3%. It's getting
One
harder and
instruction.
harder. One machine instruction. I did everything I could. Like how, right?
I lost at like V6 or something. Just to be clear.
Yeah, and then I looked at that, and I'm like, oh, it's the branches. And I knew that the branches could be a problem, but I didn't expect how much of the problem the branches were, because it was clear that if you go even further branchless, you will have to invest more machine instructions. And I did at some point during the contest some experiments on it, but it didn't seem to pay off. But apparently after all these optimizations, it was the case that we are completely bottlenecked on the branches. And the thing there is, if you go back to the previous Perf, to this counter starts, you see here that about 6-7-8% of all branches are missed. And if you look at these values here, these values tell you what was the reason that a certain instruction couldn't be finalized, couldn't be retired, couldn't be performed in some ways. And you can see here that one of the main reasons some instruction couldn't be performed in 40% of the cases is because of bad speculation. It's because we were going down a line and we were speculating on the wrong path. So Intel always speculates on branches, right? Everybody knows that since the Spectre attacks, right? And so it always tries to speculate on something. And if you look at my solution, that's the
Where did it go?
where do you go? Like this. Oh, here again. Okay.
That's not good. That's not my favorite icon.
That's the rotating pizza of death.
Any IntelliJ experts?
Let's kill it and yeah.
Demo effect.
Yeah, let's kill it and start it again, right? I mean, that's the.
Oh, bye. Yeah.
So in the solution V9, that was highly optimized, but it had one issue, which was that I talked about how I was specializing for the case of 8, length 8, length 16, and the rest, right? The problem is that the cases of 8 and 16, it's a 50-50, and the data set is random, which means whether after you process a city of length 8, whether the next city is of length 8 or 16 is a 50% chance. And Intel's processor branch heuristics will always think, okay, last time I processed a city of length 8.
Surely, this is going to be 8 now.
The next one is also going to be 8. Which, yeah, in 50% of the cases is true. But in 50% of the cases it's false. And this means the major bottleneck on the solution as it stands here is that every second row we have a branch prediction miss. So the interprocessor is predicting going along a certain parse here, and then relatively long, and then suddenly has to back out of it again. And this was a major problem on the solution. And this is why for solution 10 now,
Who was the one who came up with doing
Branchless.
it? Was it Artisan?
No, I think it was if you have the whole. Where do you have the leaderboard? It was Jaromir.
Jeremy. Nice.
Jaromir did the Branchless.
We'll get back to it.
Yeah, Jaromir. So now, if we look at how the solution had to change, now the solution in general stayed the same, but in this one aspect of parsing of the parse loop, let me scroll to it first. Here's the main method. Find the result, scan number. No, it's not here. Wait a second.
It's below that. This.
Yes, here we are. Find result is the method we are looking at. So now here, before we saw here the cases of 8 and 16 differentiated by a branch. But now we are no longer want to differentiate those two cases by a branch.
We just process.
We want to process those two things together in one go. Okay? This means, of course, for the 8 case, I will have to do more comparisons than needed because I will have to compare 8 plus 8 bytes. Whereas previously I could just have one, only 8 bytes compared on the 8-byte case and 16 bytes on the 16 bytes case. Now in the 8-byte case, I also need to compare 16 bytes, and I just need to make sure I'm masking out enough of the things that are not city names that the code still works. And that's why we have extra mask arrays where one mask array is used to mask out the end of the name. I have a name string that's somewhere between 0 and 16 bytes, and I have that name string in 2 long values. And so the end of it I can mask out with this array here, where I'm just either taking the last byte, the last 2 bytes, last 3 bytes, last 4 bytes, last 5 bytes, 6 bytes, 7 bytes. And whether I'm in the 8 or the 16-byte case, for this I'm using that second mask, which means either I'm considering the second 8 bytes of the string, or I'm not considering them at all. And when I'm not considering them, I'm just masking them away. So masking away means I'm just ending, I'm using an end operator with the value in this mask. And if the value of the mask is 0, obviously I'm just erasing those bits. And this is why then in the code here, I have the 2 letter counts, the letter counts for the first 8 bytes and for the second 8 bytes. And then I'm using masks to make sure that the word number 2, I have 2 words. The first word is the word, I have 2 words for the city, right? And I just need to make sure that for the 8-byte case, the second word is masked out. Such that then, when I'm doing my collision check on the hash table, I can use the first word and the second word without any branching whatsoever, because I know for the 8-byte case that I previously distinguished by branch, the second word will be 0, because it's masked out by these masking tricks before. So in the end, it's a
You don't do too many things double, because you already needed to mask out these bits for calculating the hash code and for comparing. So
Right.
it's only doing the second thing that's
right.
and it's not that much overhead. So
Yeah, and interesting enough, right? I have here additional memory accesses. Like these are memory accesses into arrays even, because they're static final long arrays, but it still will be a memory access. But even those memory accesses into arrays do not seem to affect performance enough to counter the removal of the branch. So it's in this case not, because the array content is not final. So there is no way the compiler knows that the array content is final. They are not going to be inlined. And it will not help that much, because the array itself anyway is going to be very easily accessible, because it's always going to be in cache, because you're always going to hit this part of the program.
Don't look spoilers.
Yeah, no spoilers. Yes, this is again the just on the slide, these two elements that were then used to get that solution into a non-branching one. And it is really surprising. So this is the perf stats for the final solution compared to the, and we will compare it to the last solution, to the second last solution. And now suddenly the amount of instructions that are going to be executed here, we are executing now 117 instructions per row. So we are executing 17 more instructions per row than before, because before we only executed 100 instructions per row. The amount of cycles, however, the processor takes to execute those instructions is now only 41 per row, and previously it was 52. And the branch misses are down to a very low number. It's now only 3 branch misses every 100 rows. So 1 every 30 rows is a branch miss. And before, we had every second row a branch miss. And if you take this together, those two calculations, yeah, so before we had 52 billion cycles, now we have 41 billion cycles. Before we had 100 billion instructions, now we have 117 billion instructions. Before we have 500 million branch misses, and now we have a very small number of branch misses, negligible number. So this indicates that the 17 instructions more per row, they should be about 5 cycles, because it should be about 3 cycles per instruction. 3 instructions per cycle. And we have half a branch miss less per row. And those two things together means 11 cycles less per row. So despite doing 5 cycles more work, we have 11 cycles less per row. And we are saving a branch miss every second row. And from this calculation, we can conclude that one branch miss seems to cost, at least for this example here, 32 cycles. So I can do 32 cycles of work more to just save one branch miss. And this was, it's clear that branch misses are bad, but
Rio we already said that in slide 20 or something.
yeah, we always said in
misses
Mandate.
branches
branch
are
misses
always
are bad,
bottleneck.
right? But this just shows how bad they are, right? And of course, here it's the worst case scenario for the processor, because it's a random data set, and so you really have
It's
this
the
lot of
50-50 that's really messing it up.
Exactly.
It's the worst case.
But it shows you that when you run your program with perf and you see a lot of misses, you have a lot of optimization potential, because branch misses are such a bad thing for the Intel processor. And saving the branch misses can help a lot. And this is why branchless code is to be preferred. Yep. Right. Yes,
and even if you have
the pipeline is so deep nowadays in very modern processors, the pipeline is so deep that the cost is so high.
Yeah, and even if you have branches, if you have a way to make them more predictable, that's also a big plus.
Yes,
so
a predictable branch is
because
a branch that's 100% predicted is 0 cost.
Yeah, exactly.
Very low cost.
Exactly.
And this is why if you have a normal Java program, a lot of the branches are actually predictable, because a lot of the branches are related to bounce checks that would never fail, or an array bounce check should never fail, and therefore Intel is very good at executing such type of code. But it's obviously very bad if the branches start to actually fail. And this is a statistic I did on the 10 versions of the solution, and we can see how well the first solution submitted. The number of instructions per cycle was also relatively good because the code was so bad, it had so many bounce checks in it, where the Intel processor was always predicting it correctly, that it could actually fill up the pipeline and could hide some of the badness of the code. As then we optimized the solution to get better, instructions per cycle was falling and falling and falling because we removed like really unnecessary work that Intel was hiding from us. And then the most obvious thing on this graph is that for the last solution, we are really getting the bad speculation percentage from 25% down to 0 for retiring instructions, and getting the instruction per cycle from 1.7, 1.8 to 2.4 was what gave the final speed up of 15%. The final speed up was 15% because well, there were more instructions to be executed, but the savings so big that they outweighed this additional work. Right, yeah, and
this is something we both didn't use.
Right, we didn't use Vector API. Now,
there's a good reason.
One reason for that is that GraalVM JIT compiler.
Let's first explain what are we looking at. This is I've never seen Java code like this.
So this is the new Vector API. It's currently in incubator status. They will continue to be in incubator, I think, until Valhalla is finished. Mm-hmm. And it allows you to. Well, one of the things used here is the foreign memory API with memory segment. And it is then creating a memory segment and it is creating a byte vector. It is taking a byte vector, the largest byte vector that is native to the platform, and is then doing a vector comparison to search for that semicolon. Yep. Because so a lot of the tricks we did.
Basically, what we were doing with SWAR, there's actually a better way to do this.
Yes.
Using factorization.
Yes. A lot of the tricks we did around SWAR and around the long values was to avoid the need for vectors. And these vectors, it can get easier. And vectors will be faster here specifically for the cases where the city length is longer. So if it's 15, 16 or 32 bytes, then suddenly the vector will be faster and faster. If a lot of them are very small, then the vector code is not going to be that much faster. But the Vector API would certainly be here the next step to get the Java code even better. And we are currently working to make sure the Vector API is translated into the correct machine code on GraalVM and GraalVM native image. We still have some compiler work to do there to make this run efficiently. But I'm working with the team there, and I'm optimistic that we will soon actually present a 1 billion row challenge solution that runs even faster on Java.
Nice. So step-by-step progress you can see in the execution time and lines of code. The code got more complex each time, but the times started to stumble, like really tumble all the way down.
Yeah, these are all the versions we went through.
Compared to 100%, right?
And you can see sort of how it was starting to get a little bit harder and harder to push further. But I always thought, whenever you think there's no more, it's 10% more. And I was glad the contest finished.
Impact. And in the end, congratulations, Thomas. You won.
Well, congratulations to Juan and Alfonso as well, who
but
it was a team that
won. But everybody used code from each other.
Yes, and almost everybody used the Graal compiler, which is
exactly
the main win I was looking for.
Yeah.
So from that perspective, yeah, it was fun. It was a lot to learn, also for anybody participating. And it was really great that different participants could bring different perspectives and different ways to optimize this. No, I think it was great. And in the end, the solution, ran on 8 cores in 1.3 seconds, 1.5 seconds.
Yeah.
Which we were like, during the contest, at some point we were like 2 seconds is the limit. Nobody's going to go below 2 seconds.
But yeah, whenever you think it doesn't go anymore, yeah, you find another 10%.
Yeah.
On stronger machines, it was even up to like 300 milliseconds on my local machine with 32 cores.
Yeah.
And it shows that Java is good at also batch processing. Java is good at programs that run very small, like for very short periods of time. I just found, I just saw recently on Twitter somebody said, "Oh, Java's not good for command line applications." Of course,
Yeah.
you can process a billion lines of code in billion lines in 1.5 seconds.
Of course, you can make.
No,
command
Java
line.
is absolutely good for that.
Yeah.
It's absolutely no problem to get to the best startup here and also the best peak performance.
Yeah. So before we continue, there were also people in other languages like this. Do we have a slide about that? I think we have, right?
I think it's
Later,
later. Yeah, there is some blocks here, right?
So,
But there's other languages that participated as well, like not in the competition, but participated on the side. You are measuring on their own machines and so on. But I mean, the only way people could get faster at the very end was with inline vector assembly.
exactly. I've seen solutions in C# that use even more vectorization than we can currently do with Java.
Yes.
And they can run in like 0.9 seconds, etc.
Right. Yeah.
But
So vectorization certainly is
it's
the
very
next
close.
step, and we are working on that it also works here for Java, and it would get you then a little bit more.
So one of the things you mentioned this morning was how can we have a DevOps talk this year without AI?
Yeah, that's true. That's true. I was, you know, I was very motivated for this contest as well because when I was younger, I was participating in Informatik Olympiads, and it was very competitive programming. And recently, I heard that ChatGPT can do that as well. So we entered into ChatGPT the question: "Can you solve this for me, please?"
Let's just try and solve it without.
Yeah, let's
telling
ask
it.
it. Let's ask it. Right? It's. So you entered. What did you post?
Just the
it
website.
Was the exact,
it's the main website.
It was the exact description on the website for the task.
Oh, it's not even giving me code. Why it's not?
Ask it to give it code.
Yeah, wait.
Just ask it.
Let's switch because we tried it this morning.
Well, AI is not so reliable. Just ask it as a follow-up question. He will give you the code.
Wait. But I need to. Let's give it like at least the beginning.
No, we don't need it. I think it's going to be fine.
But we need the header because otherwise the whole code will compile.
Right.
Start from this. So I'm using the new canvas function, which is really cool. Let's see what it comes up with. Let's try it. Are you ready? Oh, it's zoomed in. So,
right.
Does it run? That's the first question, obviously. To run, we can basically wait. We can just evaluate. Let's see what it does.
Well, it runs, but it doesn't seem fast.
It's not even.
Oh, it's not even.
It didn't even copy in the header file.
Yeah.
Which is needed. I even gave it to
it's
him.
It's not at 100% there, Roy. It's okay.
No.
But it's interesting that the solution that's presented, and I tried it as well separately before. It looks very similar to the solutions that are submitted. Now,
it looks very similar to the baseline, and maybe the first optimization.
Yeah, it looks very similar to it, right? And I'm wondering if there's supposed to be a knowledge cutoff before, but I'm not sure whether that's also honored for code, right? So yeah, I think Roy, this AI thing is, I think it's still valuable to be a good programmer.
Yeah.
And I think I tried it at home, and then he gave me a solution that was the most primitive solution it did produce. It was very similar to reference, but when I asked it to make it faster, it couldn't do it.
No.
So
And actually, Antonio, you did the same. I don't know, is he here? Antonio did the same thing, and he came to the same conclusion earlier this year.
Right. So it's still a valuable skill set, and I think it's still valuable to.
Absolutely. We still need developers.
That's right. We still need developers. That's good. Yeah. So for this presentation, I put up a repository. It's called 1BRC-steps. If you clone this repository, you will see the code of all the 10 versions that were captured in this presentation, and you can run it and experiment with it. And that's just covering the most important parts of the presentation in case you want to look at more at home. Yeah, and if you want to look at more at home,
Yeah, so Gunnar has this entire repository with all the entries of everybody, but he also has like this entire list of people who wrote blog posts about it, did it in different languages, using different data sets, all kinds of stuff. A big round of applause for Gunnar. I don't know if he's actually here. He should be arriving today,
Well,
later today. He's there! It's for you, Gunnar. If you want to learn more about basically organizing this, not a lot of technical depth, but more about running this contest and,
Yes.
and information, we are going to do a conference talk on Thursday about the same topic without all the technical.
yes, this will be more about Gunnar complaining about the participants cheating and
About how amazing
asking
the
for
community
things.
is. About how amazing the community is.
Yeah, exactly. No, but it was an immensely effort from Gunnar,
Yeah.
and I think it was great for the whole Java community to come together and show how Java is fast.
And the big question is, will there be a next one? Who knows? Who knows?
Who knows?
He is kind of signaling out, who knows? Are there questions?
So he said using modern Java, right? And here you all went and used unsafe.
Yeah.
How far do you think you would have gotten if you actually obeyed the instructions and did not use unsafe?
Yeah, we can. I mean, this is very easily answerable, which is
Yeah, the question is, we
sorry.
should use modern Java, but you're still using unsafe, and that's not very modern. How far could you possibly get
without
without
unsafe and only modern Java, like without unsafe. It's very clear. It is at least V1, like the V1 version here does not use any unsafe whatsoever. It just uses standard Java APIs. And you get down here to 5.6 seconds from 125 seconds. So it's 95% of the way you're getting.
And I'm pretty sure there are other optimizations.
You can probably go further down.
Yeah. I think 4 seconds would probably work.
Yeah, you can get a little further down. So, which means in most cases you won't need unsafe. It's only for very specialized cases that unsafe is relevant there. But I mean,
And also, that one isn't using the branchless temperature parsing and other stuff, right? So,
Yeah,
so
exactly.
it doesn't even do any bit magic.
But you will start to be dominated by the checks in the end, right? Even if you optimize the rest, but you will probably get down to like about 3-4 seconds. But in general, if I would be given this type of problem at work, I would have probably stopped at the version 1 of the code.
Depends on the use case, right?
Because the version 1, I mean, was basically, from an effort perspective, was only 10% of the overall effort. It was very fast. It was optimizing a little bit the data structures, making sure everything runs in parallel, and then it was, in most cases, it was totally fine. And the furthest I would have gone if somebody really pushed me hard at work and said, like, this code really needs to run fast, I would have been here at the version 3. So I would have probably introduced unsafe, and I would have probably done a little bit of more checks at the same time. But anything beyond that is
It's the full mathematics nerd. That's where you draw
yeah,
the
that's
line.
that's where I draw the line, I would say. On the other hand, of course, in the contest, at least for me, learning about some of the concepts below are interesting to know about. Yeah, the kernel can be the bottleneck as well, right? Or it's I don't think it's completely useless knowledge to know about the other things on the bottom. But in most scenarios, of course, you will not need them, and that's in general also for the whole code here, right? There were certain aspects like the accumulation of the result at the end that didn't matter for performance, And so we didn't spend any time optimizing these parts. Even from the code of the contest, you should really only optimize the code, the code parts that are
Something is
important for
being
you.
executed a billion times, something's being executed once. Where do you focus your time?
Yeah.
It's obviously the thing that's being run a billion times.
Yeah, but even, I mean, once, even 10,000 times. Like this one loop is executed 10,000 times, but it doesn't matter because compared to the 1 billion loop, it doesn't show up in the profile. And that's why even before, certainly before you go to beyond anything than V1, the version 1 here, you would do profiling your app, and you would make sure that it's really, really important that this code is performing the best. But yeah, you know, using the Graal JIT compiler, Graal native image, and using version 1 optimization is where I would have stopped.
Mario.
Yeah, I was wondering if it will be possible maybe in a later Java version to replace the use of unsafe with the FFM API.
Yeah, so the question is, can we, in a later Java version, replace unsafe with FFM?
In theory, yes. In praxis, the problem is, I tried it also here, right? The problem is, and I had it on the slide here, yeah, this is the problem. This is showing currently the compiler graph that I later showed in the tool on a single access on memory API. And there's actually a lot of checks. There is a check on the length, which is the first check on top, right? You see there's a length loading and then there's a check on top. There's a second check on the scope of the memory segment. There is a third check on the owner of the memory segment, and there's another check on the state of the memory segment, because it could be in certain states.
So you are paying for safety.
Yeah,
Exactly.
you're paying there
Yeah.
for safety like a lot, and I think this would be probably even slower than the byte buffer checks, because the byte buffer checks are less, I think.
Francesco is dying to say something.
Yes, because the byte buffer one is what they use to implement the same algorithm within and it wasn't working because of the order. So in the current implementation, you gave up on using compact, for example,
Hmm.
because it's using a leader of bytes because it's not taking care of the entries. But the byte buffer API is currently, you know, it gets longer, you should check against the entries as well.
Yeah, exactly.
It has even additional.
Yeah, so Francesco is saying there are certain things that byte buffer does additionally that memory segment doesn't do. For example, check on endianness, which
Right.
yeah.
Right.
So there's always overhead, and that's good because we want security. We want secure code, and we want code that doesn't randomly read and write in your memory.
Yeah, no, and the memory segment API for sure has advantages, but at least in its current form, I don't think it's possible to get it to the same performance as unsafe, because I don't see where the additional checks would go away.
Yeah. Are there other questions? There's someone with their hand there.
Yes. Yes, there is one solution in
Serkan?
OpenJDK, which is solution
Serkan
number
also?
4.
Just let's look it up.
Yeah, there is two solutions using OpenJDK. So the solutions using OpenJDK here are the ones that are using the vector API very heavily. And this solution, actually, we tested it, the one that's the top solution with OpenJDK.
This is the reason.
It runs now faster with Graal JIT since the latest version, because we added the support for vector API.
Yeah.
But the reason it couldn't use the Graal JIT there was because our support for vector API preview feature wasn't enough from a performance perspective.
Yeah. So these are the things that you can do we couldn't do in Graal at the moment.
Yeah, and the one thing we're currently working on still is to make this work not only on Graal JIT,
It's
the
this.
vector API, but to make the vector API also work on GraalVM native image. And then I think this solution should be faster than the top solution. But the vector API, it's still in preview, it's still an evolving API, and therefore for us as a GraalVM developers, it's sometimes difficult to keep up with its current development and make sure that it's fully supported. But it's definitely necessary to get to the last, to further. If you want to go further on performance, you have to now go to Vector API.
There's a question right over there.
I know that hardware was set to the starting challenge. However, do you know any possible gain from running it on the GPU, for example? No?
Running it on the GPU, I think the problem is that it seems the problem statement a little bit too difficult to run on the GPU. I think it's a little bit too irregular because the problem is that the length of the rows that are processed is random. I think if you would fix the length of the rows and say like every row has length 100, I think you could probably be faster on the GPU. But I think the problem is that currently, in order to pass the next row, you have to parse the previous row first.
Yeah.
And that's a big issue in terms of maxim out on the parallelization. Exactly. I think that's the main problem. I mean, I'm not a GPU expert, but that would be my guess on.
And there are certain things you could do.
Yeah.
Like for example, parsing the bytes and turning it into integer temperature. That would be perfect to do for everything at once. But once you start collecting things and basically putting it in a hash map and counting things, that's also where the GPU stops, I think. So there are certain steps, like pre-processing steps that you could do, but after that, probably not anymore.
Yeah, but anything on parsing, you would have to get much more regular in terms of the parsing structure, I think, to get there.
Gunnar's taking notes. Yeah, question here.
You already mentioned Valhalla. The Graal compiler does a lot of the optimizations that will be possible on C2 with Valhalla as well, like deep threading and other things like moving objects when they don't escape.
Yeah.
What would you say would like the simple solutions would benefit from using value types both on C2 and on Graal JIT from the perspective?
Okay, yeah. So the question is, how will Valhalla benefit simpler solutions of the problem here, right? So the main area where I think Valhalla has the ability to benefit is if it can make the data structure of Java util hash map more efficient. Because currently using Java util hash map is a problem for the performance because of this. Objects that are allocated per hash map entry. And I think one of the intermediate goals of Valhalla is to make sure that those objects are potentially inlineable into the hash table array. And that would certainly help that we could use the standard hash map implementation without problems. I think that's the main thing. Now, you mentioned a little bit that Valhalla and escape analysis are connected. Now, this is not necessarily the case. Like escape analysis is an optimization that we can already do in the compiler without Valhalla because we can prove the local aspect of an object. Now Valhalla can help us in the future is areas where we can do actual object inlining, for objects that are escaping the current compilation and where we need to have a flat array, for example, or where we need to have one object inline into the other. And I'm really hoping that we can get there because it would also help then the data structure of my solution. Like my solution's data structure is currently like it's currently result objects in a result array, right? So let's go here. If you go here, right, and you go to this solution here, then it's actual. I think it's on the top here, yeah. That's baseline, that's B1, right? Yeah, so on the top, it's actually result objects in a result array, which is here. So this is the result array, which is my hash table array, right? And currently, this is objects in that array, and this array will be one of the prime arrays that with Valhalla, hopefully, we can then have this array flattened and the entries into that array not being objects. And that will be a cool thing, and it might need to have some coordination with escape analysis. But the main aspect that I'm looking for when I think about Valhalla is allow me this different memory layout for arrays at least, and maybe then also for objects. Yes. Currently there's a memory indirection in my solution here, where I'm going from, like, I first have a cache fault potentially, a cache miss potentially when I'm accessing that results array, and then from the result array I need to go into another memory area which has my result objects.
You could just use one big byte array and write with unsafe.
Yeah, that's what that's what these guys have been doing. But I'm actually surprised that it's not so much of a performance difference and that the solution could still be the top solution with that indirection in place. Because as we saw, every machine instruction counts, and I'm pretty sure if I would refactor it to this solution, which I'm not doing because I'm refusing.
So it's better.
It would be a few machine instructions, probably less, like maybe one, 2 instructions less, right? But in general, I mean, Java garbage collectors have gotten a lot better over time, and then you get some additional memory density still. Also, you have more hops, you have more indirections, you have memory density. But this is the area where Valhalla should really help. Because if the memory layout can avoid that hop, can avoid that indirection, that would be really cool. We have, for example, an optimization in Graal native image where we are doing inlining of the string jar array into the string object. So currently when you access a string in Java, you go to the string object and then you have another indirection to the string byte array. This is another area where getting rid of this additional indirection in the object layout would help.
One question here. There are also questions in the back, but I can't see them. I'll come back to you.
We're talking a lot about the cost of taking these jumps, right? The indirections. Is there a way to get numbers on that? Like, is there some way to ask Perf to say, like, hey, to which extent are we paying for these memory indirections as opposed to,
to which extent are you paying for memory interactions? Yes. So if you look at the perf output here again, like what you need to look at perf is this the TMA, which are these different reasons why the instruction couldn't be retired, and you will see here, like if you have too many misses on the caches, you will see that the instruction per cycle will go down a lot. Like the on top here, the instructions per cycle will go down because an instruction cannot be scheduled because you're waiting for a memory input, and you will be here. You will see here that you cannot retire enough instructions. So the warning sign for you that the main warning sign for you that you're not using the processor appropriately and that you might have a memory problem is a low instruction per cycle count.
Yeah. Now I can actually see. There was also a question right there.
No,
Yeah.
Unfortunately not.
Well, and even if they were unique, you were not allowed to use that. Because Gunnar really stressed out, you cannot make any assumptions. If the first bytes seem unique, then maybe somewhere...
I mean, we could make petition to rename cities, but
So
unfortunately
we were
there's
not allowed
many
to use
cities that start with San Francisco, San Antonio, San something, for example.
Yes.
Or St. Petersburg, St. Paul, etc. So there was, in the city set, there was unfortunately not even the first 3 letters. Not even the first 4 or 5. You needed to go really long before you had an absolute unique value. And I was at some point experimenting with something where instead of a hash map lookup, you would look up sort of into a tree, like a tree lookup, that you kind of just go along a kind of a tree of cities, but it didn't work out. It wasn't faster at all. So the hash lookup was super fast because you knew that you had no collisions, and hash table is just an amazing data structure that's hard to beat even if you try to do tricks around a faster lookup.
There's also one thing I tried, which obviously failed, because I also noticed that if you break the file into 8 parts and you start processing, one might finish sooner than the other. So what I tried to implement, and I spent a lot of time on that, was actually processing from both sides, because you could just, and then they meet in the middle and you don't have that problem. But that was a lot of wasted time.
Right.
Are there any other questions?
Yes.
One.
You split up the whole process in smaller chunks. Did you consider or try out fork joining?
So the question is, did we consider using a fork join to split that? Well, it turns out if we know how many processes there are, in this case 8, it's highly optimal to just make 8 different threads and give them all equal amount of work instead of using something like a fork join pool. I might have had it in my code once or twice somewhere in the beginning, but in the end, especially if you know you need 8 threads, you just create 7 more and you already have one, then you have your 8 threads, and that's optimal, I think.
Very cool. That was a very long deep dive. Thanks everybody who could make it all through. I hope you learned a little bit. You could enjoy as well.
Follow us and Gunnar on Twitter, maybe, if next year comes around, if it's the 1st of January again, there's a new contest, and now you know all the secrets, so you can compete as well.
That's right, yeah. And Gunnar will be talking, if you want to hear more from the community side or the challenges he had with putting up the benchmarking infrastructure for the challenge. There will be a talk tomorrow.
Thursday.
Thursday,
Yeah.
yes. I will be talking tomorrow about GraalPy and Python and GraalVM. So maybe the next challenge we're gonna use Python on the JVM as well.
Not me, but yeah.
And I'll be around here. If you have any more questions, I'm happy to answer in detail.
And one more plug, I really like El Zimmerman's programming contest. A new contest started this Saturday, and it will run until the 4th of January. So perfect to kill the time until the next possible contest. Give it a try. Actually, I'm curious. I'm still third. Nice.
Oh, so we need to cheer for you.
Yeah.
All right, cool. I will. This time I will cheer for you.
Challenge me. That's it. Thanks.
All right. Thank you very much. Thanks for your attention.
If you like to talk, don't forget to vote.
All systems are nominal. Initialize Genesis sequence.